A comet from another star just lit up James Webb's cameras, and it's packed with way more carbon dioxide than water. It's racing past the sun, growing a strange tail, and breaking the rules we teach in science class. Experts say it looks natural, but a few clues still don't fit neatly in the box. So what did Webb really find? Is 3I Atlas just a weird comet, or our first hard hint of alien tech? Imagine a cold spark moving through deep space, a tiny dot against a black sea. And then imagine what happens when that dot steps into our sky. James Webb turns its gold mirror toward the stranger and breaks its faint glow into colors we can read. The story in those colors is simple and bold at the same time. This is a real comet from another star, a traveler on a one-time path, here for a short visit and then gone forever. It is fast, near 60 kilometers each second, which is about 130,000 miles each hour. It is big too, with a solid heart about 11 kilometers across, roughly 7 miles. A mountain of ice and dust hidden inside a soft cloud. It moves on a curve that never closes, a hyperbola. So the track tells us it is not bound to our sun. You can feel the tension in that shape, like a sling stone flying free. The first taste of sunlight wakes it, and gas begins to rise from tiny vents. Grains of dust lift and drift, and soon a pale coma swells around the dark core. A thin tail grows and points away from the sun. Pushed by light and wind, you cannot see but the comet can feel. All of this is classic, and yet the mix of gas is not what our books would guess first, and that twist is why even calm scientists sit up straight. Webb's instruments act like a prism and a nose at once, splitting the glow into lines and letting us sense what is there. We see water, the old friend of comets. We see carbon monoxide, another common gas. But we also see a lot of carbon dioxide, far more than the water by a wide stretch, like 8 parts to 1. If noses could work in space, the smell would be sharp like dry ice. This rich carbon dioxide means the comet may have formed in a colder or stranger zone around its own star, where water froze deep inside and carbon dioxide sat closer to the surface. It may mean crusts and layers that push one gas out first and trap another until later. It may mean that planet systems far away build comets in many ways, not one way, and that is the kind of news that grows new ideas. The size is not a guess pulled from thin air. It comes from how bright the core seems after we remove the glow of the cloud, and from how the light fades with distance. The speed is not a wild shout. It comes from many nights of tracking tiny shifts against fixed stars and solving the numbers. The path is not a rumor. It is the curve that fits those points best. The math drawing the same open arc again and again. Even the time of day for the best view is set by the sun. When the comet swings closest to the sun, around 1 4/10 astronomical units, the glare will hide it from Earth for a while. That sounds sad, but it adds to the drama, because we will watch it hard before and after, and craft a clean story from both sides of the bright wall. Mars orbiters may see what we cannot. So the sky itself becomes a team, with one set of eyes taking over when another must blink. Feel the contrast in your mind. Think about a normal comet from our own deep cold, where water rules and carbon dioxide is only a helper. Now think about this traveler, where carbon dioxide seems to lead and water waits. In one, the kettle boils at a certain range from the sun. In the other, the boil begins sooner, even when it is still far out and the light is thin. That early breath is a clue. It tells us the skin is different, or the layers are stacked in a new way, or the birthplace had rules not like ours. This is how a single object can change a whole field, not by breaking physics, but by showing more of what physics can do. The tail could reach millions of kilometers into the dark, a soft brush stroke that always points away from the sun. You would not see the 11-kilometer rock and ice inside, but you would feel its presence in the way the fog behaves. James Webb does not see feelings. It sees heat and light, and that is enough. Webb hears those notes and measures how loud each one is, and that is how we know the mix. We also know what it is not. There is no steady push that would show a motor. There are no narrow radio beams that would shout a message. It is a comet, natural and free, and that is exciting all by itself. Still, the mind loves to test the edges. If a craft ever came this way, what would prove it? We would look for heat that rises and falls without the sun's touch. We would look for timing that repeats with a plan. We would look for gases that match fuel more than ice. Hold the long view for a moment. This object likely slept for ages near 400 degrees below zero. Its skin took hits from cosmic rays and tiny dust, and a dark crust may have formed that holds heat like a thin blanket. When sunlight finally reached it, gas broke free through cracks and pores, and the blanket puffed and tore. So we stay careful. We use numbers and repeat checks. We share data across teams and telescopes. We admit what we do not yet know. And we say what would change our minds. Here is the heart of our hook, and it beats steady. A gold mirror in deep space looked at a quick, wide wanderer from another sun and found the clear signs of a comet. A coma that swells, a tail that points away, and chemical lines that match ice turning into gas. The twist is the ratio, the extra carbon dioxide, which hints at a birthplace or body plan that is not like our usual case. This hint does not end the story. It starts it. It points us to more tests we can do as the comet moves in and then out again. We will track the gas mix as distance changes. We will watch the dust counts rise and fall. We will use Mars to see when Earth must look away. Most of all, we will keep the light line between wild guess and fair claim. That is how a short visit can teach for a long time. So listen with us. Feel the numbers as part of the scene, not instead of it. 60 kilometers each second. 11 kilometers across. One trip through and gone. A cloud that smells like dry ice if noses could work in space. A tail like a gray ribbon, always away from the sun. A voice in infrared that says, "I am a comet, but I am not like the ones you know best." Stay with us as numbers become pictures and pictures become truth we can trust. Step closer now. Think of a guest who walks through your front yard, never slows down, never stops to talk, and never comes back. That is what 3i Atlas is to our solar system. It is an interstellar visitor, which means it came from outside, from another star's neighborhood far away, and it will not stay. Most comets we know are family. They circle the sun again and again, like runners on a track. Their paths are closed ovals called ellipses. But this one is different. Its path is open. The math that fits its motion is a hyperbola, a long curve that comes in from the deep and then bends away forever. You can picture it like a stone thrown past a campfire. It warms as it passes. It glows for a moment. And then it is gone, into the night. We have seen only two other guests like this before. The first was Oumuamua in 2017. It was small and faint and strange, and people argued about its shape because we only saw light getting brighter and dimmer as it spun. The brightness changed in big swings, as if the body were long, like a chip or a stick, or maybe flat like a pancake. It did not carry a big dusty tail, and that made everyone curious. The second was 2A Borisov in 2019. It looked more like a classic comet, with a steady coma and a tail that grew as it neared the sun. It smelled, in a science way, like the cold places in our own system, with common ices turning into gas under sunlight. Those two taught us that visitors can come, and they can be very different from each other. Now we have a third, and it is larger and louder in our instruments, and its message is clear enough for even careful minds to lean closer. To understand why this matters, feel the difference between ours and not ours. The comets that live with us were born in our sun's disk long ago. Their ices and dust formed from the same cloud that made Earth, Mars, and the rest. They carry our local story in their mix of water, carbon monoxide, carbon dioxide, and organics. Their orbits are tied to the sun's pull. They come back on time like a bus you can set a watch to. An interstellar object breaks that pattern. It carries the story of some other star, maybe older, maybe colder, maybe built with a different recipe. Its speed is high, even far from the sun. Its track is too open to close. Its past is in a different sky. The I in 3I Atlas stands for interstellar. The number 3 means it is the third one confirmed. The name Atlas comes from the survey that spotted it, a set of wide-eye telescopes that scan the sky for moving points, night after night. They look for the tiniest shift against the still map of background stars, a shift you can measure in arcseconds, which is a very small slice of a degree, like the width of a hair held at arm's length. When those pixels jump just right between two images, it means something is moving fast nearby. Then the alerts go out. Other telescopes swing over. The dots become a track. The track becomes numbers. The numbers become a path in space we can trust. The path for this object does a careful dance close to the sun's plane. The angle is small, only a few degrees off the flat sheet where most planets move. That is unusual for a visitor, but not proof of anything spooky. Space has many dice, and even rare rolls can happen. The key fact stays simple. The eccentricity is greater than 1. In easy words, the curve is too open to bind. The sun cannot keep it. The speed stays above escape speed even far away, around 60 kilometers each second when you measure the excess, which is the speed left over after gravity does all it can to slow the traveler down. This is the clean sign. This is how we know it is not from here. If you close your eyes and feel the numbers, you can sense the tension in the visit. Far out, the object is cold and quiet. Skin near minus 240 Celsius, close to minus 400 Fahrenheit. It is as black as fresh asphalt, darker than charcoal, so it reflects only a small slice of the light. As it falls inward, the sunlight grows 4 times stronger each time the distance halves, because light follows the inverse square law. At some point, ices start to lift as gas. Dust rides those jets into a fog. The coma forms. The tail begins to stretch, always away from the sun, pushed by the solar wind and light. This is the same story for most comets, and yet it is happening here for a visitor that will never give us a second chance. One pass, one set of tests, one window to learn. Remember the 2 older guests to build the contrast. With Oumuamua, we had mystery and low signal. We argued over shapes and tiny non-gravity pushes that might have come from gentle outgassing we could not see. With Borisov, we had a clear comet with water and carbon monoxide that matched our models well. With 3I Atlas, we get a mix of both. A visitor that is clearly comet-like with a bright coma and tail, and yet with gas ratios that make us blink. But that detail belongs to later acts. For this moment, hold on to the identity. It is a comet from another star. It is the third we know, and it is on a one-time path. If you want a picture that fits in your hand, imagine a snowball the size of a city mountain, about 11 kilometers wide, wrapped in dark dust. Now imagine throwing it past a bonfire so huge it lights a whole world. As the snowball passes, its skin smokes. Not with flames, but with vapor you cannot see. The smoke blows away from the fire. Ash lifts and rides the flow. The snowball curves and vanishes into the night. You can stand by the fire only while it is there. When it is gone, the night looks the same, but you are not the same. You know more about the kind of snow that comes from other hills. There is one more layer to this act, and it is the quiet pressure of time. Because the path is open, there will be no return. That means all our plans must fit into a slice of months. We must choose the best nights, the best filters, the best instruments, and we must share the results fast. We must look before the sun's glare hides it, and look again after it clears. We must compare what we see with what we saw from Oumuamua and Borisov, and with what we know from our own long-period comets that drop in from our distant cloud. We must ask the simple, hard questions. What makes a visitor start to vent? How soon? How strong? Which ices go first? Which dust sizes fly best? Each answer is a clue, and each clue points back to a birthplace we cannot visit, a disk around a star we may never see. So hold the idea steady in your mind, like a marble on a string. 3I Atlas is the name. Interstellar is the class. Third is the count. Hyperbolic is the path. One pass is the rule. It is not ours. It is here now. It will leave soon. And in that short sweep across our sky, it can tell us how other star systems build small worlds, how cold places store their ices, and how a universe full of paths can bring a single guest to our door just once, at just the right time to teach us something new. Start with a number you can feel. 11 kilometers across. That is the best size for the hard heart of 3I Atlas, the hidden rock and ice under its soft fog. 11 kilometers is about 7 miles, longer than a line of 1,000 school buses end to end. Picture a dark hill the size of a small city, wrapped in soot, turning slowly in a black ocean. Now give that hill a speed you can taste in your chest. 60 kilometers each second. That is about 130,000 miles each hour. In the time you count one, it has rushed the distance from one side of a big town to the other. It is not strolling. It is a whistle and a blur. It is a fast stone that the sun can only bend, not hold. How do we know these numbers and not just guess? We use light as a ruler and a clock. When the coma is thin, some starlight bounces off the core and reaches our mirrors. That gleam is faint because the surface is as dark as fresh asphalt and throws back only a small slice of the light. But faint does not mean useless. The dim tells us how big the core must be to reflect that much light at that distance, if it is that dark. Change one part of the guess, like how shiny the skin might be, and the size changes too. Check again with other colors and other nights. Peel away the glow of the gas with math, and the answer keeps coming back near the same place. 11 kilometers. Not a pebble, not a planet, a mountain in motion. Speed is a different kind of truth. Telescopes watch the dot slide a tiny bit against the still map of far stars. The slide is measured in arcseconds, little slices of a degree so small you could hide many under a single grain of sand held at arm's length. Take that motion and the time between pictures, and you get an angular rate. Combine that with distance, and the rate becomes real speed across space. Watch it longer, and the curve of the path appears. Fit that curve with the math of gravity, and you can tell how much the sun bends it, and how much speed is extra. The extra is called hyperbolic excess velocity, the leftover speed after you give the sun every chance to slow the traveler down. For this guest, that excess is near 60 kilometers per second, even far from the warm light. That number sits above escape speed, which means the sun cannot keep it. It came from out there, and it will head back out. Feel the mass behind the motion. If a chunk 11 kilometers wide is mostly ice and dust, it could weigh more than 1 trillion tons. Pack that much stuff with that much speed, and you have a moving store of energy that could melt a mountain or boil a lake if it ever hit something solid. It will not hit Earth, but knowing the size and speed helps us plan how to watch it safely with eyes and ideas. The speed says the show will change day by day. The size says the supply of gas and dust is deep, so the fog can grow and shine for months. Size and speed together make tension in our plan. We have time, but not a lot. The window is open, but it slides fast. Use your hands to weigh and your eyes to scale. Hold a marble for Umama, the first interstellar visitor. Small and strange, maybe 100 meters long if it was long at all. Hold an apple for 2I Borisov. Closer to 1 kilometer across, a classic comet in a small package. Now place a bowling ball in your other hand for 3I Atlas, heavy and firm, and then imagine making that bowling ball as wide as a city. The jump in size is not just a fun picture. It means sunlight digs only a short distance into the skin, so the inside stays cold as the outside begins to vent. It means cracks and caves inside can hold pockets of gas that wake at different times. It means jets will have power to lift bigger grains, which can make a broader, brighter tail. A bigger body also turns more slowly, so one side can bake while the other rests in the dark, and that rhythm will write lines in the light we measure. Speed paints its own marks. A fast comet spends less time at each distance from the sun, so each shell of heat moves across the skin like a wave that never stops. At 3 astronomical units, sunlight is 1/9 as strong as at 1 astronomical unit, because of the inverse square law. As the comet falls from 3 to 2 to 1.5 units, the heat climbs like a drumbeat, and the jets change with it. With a slow family comet, we might watch each step for weeks. With this one, the steps race. A gas that wakes at a cooler point might sing earlier, a gas that wakes hotter might sing late, and the songs will overlap. Our instruments must be ready to hear them all in order. The speed is the reason we plan many short looks instead of a few long ones. The speed adds a quiet clock tick to every night. The path of the core also sets the shape of the fog. As the object moves at 60 kilometers per second, the dust and gas must decide to follow or lag. Fine grains feel the push of light and rush back to form long, soft ribbons. Heavy grains hang near the path like a slow spray of sand. The gas expands in all directions, but the solar wind drags the charged part into a straight blue ion tail. The faster the core moves, the more the tails bend and twist, a flag in a strong wind. Measure the bend and you can tell the speed of the wind. Measure the spray and you can tell the sizes of the grains. Size and speed echo again in these shapes, like a code we can learn to read. There is also the dance of spin. A body 11 kilometers wide can tumble with a period of hours or even days. If it spins every, say, 10 hours, and it flies 60 kilometers each second, then in one spin it travels more than 2 million kilometers along its track. That means one jet tied to one face will draw a corkscrew in the cloud that is stretched out over space, a spiral painted across millions of kilometers. Webb and other eyes can catch that twist if we time the looks right. The period tells us about the body's shape and strength. The change in period over weeks can tell us how jets push on the core, like tiny thrusters. Again, size and speed are not just numbers to brag about. They are tools to pull hidden facts into the light. Now let the scale reach into your skin. Stand by a river and listen to fast water. It roars a little, and it tugs at your shoes. Think about that pull and make it 50 times stronger, and then change water to vacuum and sound to silence. The comet feels that tug as it sweeps by the sun. The sun bends the path, but the comet keeps its extra speed. It is like a runner who cuts a corner fast but never slows down. The bend sets the day of closest pass, the distance of that pass, and the times when the glare will hide it from our eyes. The numbers write a schedule we cannot change. That is the foreshadow in this act. The size promises a big show. The speed warns it will be quick. Together they whisper, "Watch now, or miss it." At last. Bring the facts back to a simple picture you can hold. A city-sized hill, dark as coal, 11 kilometers across, glides in from far space. It moves 60 kilometers each second and will not stop. Sunlight wakes it. Gas lifts. Dust flows. A tail grows millions of kilometers long and points away from the sun like a silver ribbon. The hill curves by and heads out, still fast, still free. We will not see it again. But if we measure the size and the speed with care, the one visit is enough to tell us a long story about how it was made, where it came from, how it breathes, and why a sky full of stars can send a giant snow-black mountain past our door at just the right time to teach us something new. Imagine standing outside at night and feeling the quiet air on your face, while a small light, far away, slides across the black. People ask, "Is it coming here?" That is the first question each time a new space rock is found. With 3i Atlas, the answer is clear and calm. It will not come close to Earth. It will not hit. Its path stays far away, and the numbers show it again and again. When we turn those numbers into a map, the line never touches our circle. The guest cuts across the solar system like a bird that glides over a wide lake and never skims the water. The space from Earth to the Sun is 1 astronomical unit, or 1 AU. That is about 150 million kilometers, which is about 93 million miles. The closest 3i Atlas gets to us is about 1.8 AU, that is more than 270 million kilometers, or about 170 million miles. Light, which is the fastest thing we know, needs a bit over 8 minutes to cross 1 AU, and would need almost 15 minutes more to cover the extra 0.8 AU between us and the comet at its nearest. How do we know this with confidence and not guesswork? We watch, we measure, and we solve. Each night, telescopes note the tiny shift of the comet against background stars and log the angles and times. Computers fit those points with the math of gravity. The fit gives an orbit, and the orbit gives a timetable. Where it will be tonight, next week, next month. More measurements shrink the blur in the answer, like turning a fuzzy picture into a sharp one. The path will not jump to a new lane and cross ours. We can say that in a steady voice. At closest approach to the Sun, the comet is about 1.4 AU from the Sun, a bit inside the track of Mars. Earth, at 1 AU, is on another part of the sky during that time. Later, near its safest pass by us, Earth is still about 1.8 AU away. The Moon sits about 384,000 kilometers away. In that stack, 1.8 AU is so huge it feels like a deep ocean between islands. You might feel a little worry anyway, because the comet is big and fast, and the word comet can make hearts race. It is okay to feel that and still trust the math. Imagine a giant chalkboard in the sky. We draw the Sun at the center. We draw Earth's round path, 1 AU wide. We draw the comet's open curve, long and thin. Now we slide the comet along its line as the days go by. It never crosses our circle. It leaves the inner system, and the space between us grows even more. There is also the way the comet's speed works. At about 60 kilometers each second of extra speed, it spends little time at any one spot. A fast traveler does not loiter near Earth's place in space. It does not have time to be tugged into a new path that would cross our orbit. The Sun bends it, yes, but not enough to change the plan. It comes in, glows as it warms, and then heads out on a mirror path. We can also test what-if ideas. What if a push from gas jets changed the path? Think of a soccer ball blown by a child across a field. Now move the goal another continent away. Our goal line is Earth's orbit, and the ocean is the hundreds of millions of kilometers of space that lie between. We look for small changes and add them if they are real. There is a different kind of tension in this safe act, and it comes from how we will watch. When the comet is closest to the Sun, it sits near the Sun in our sky. We will lean on spacecraft at Mars and on telescopes that can work at other angles. Safety gives us the gift of calm planning, but the sky still sets the rules, and we must follow them. Safety also lets us think about wonder, not fear. It keeps a gentle gap. We can treat it like a rare, shy animal in a wide field. We use long lenses. We learn by looking. That is how science shows respect to the universe, by paying attention without panic. And because of the safe distance, we can invite everyone to watch, even kids, without the heavy cloud of disaster talk. Safe means we can focus on details. We can measure the tail length in millions of kilometers. We can time the rise of gas at different ranges from the Sun. We can test ideas about where and how the comet formed without the noise of alarm. The best part is sharing clear numbers that anyone can repeat. Closest to Earth is about 1.8 AU. If you like pictures better than facts, keep a simple one in your head that you can take to the yard at dusk. Put a bright lamp on a table for the Sun. Walk one big step away for Earth. Place a marble there. Now measure almost 2 steps more and put a tiny bead for the comet at its nearest to us. Even if the bead were a bowling ball, the space would be safe. Astronomers also check and recheck with independent teams. One group makes an orbit from Hawaii. Another checks it from Chile. The answers match within tiny slivers, like the width of a hair seen from a block away. For this path, it is so small that even if you slide the whole line up or down by that amount, it still misses Earth by a huge margin. The screens stay quiet. Think about the shape, too. This path is hyperbolic, which means open. It will not loop. It will visit once and then leave. Now picture the sky on a crisp morning. The Sun is bright. The comet is out there, but far to the side. You feel no heat from it. You hear no sound from it. You only see a thin tail through a telescope and a faint smudge in photos. The quiet is part of the story. Distance makes it quiet, and distance makes it safe. The numbers hold, the map holds, and our plan holds. We watch, we share what we learn, and we enjoy a safe show. Think of a clock with one special chime. It will ring when 3I Atlas reaches its closest point to the Sun, the moment called perihelion. That bell is set for late October 2025, near October 30th, when the comet will be about 1.4 astronomical units from the Sun. 1 astronomical unit, or AU, is the space between Earth and the Sun, about 150 million kilometers. So 1.4 AU is about 210 million kilometers from the Sun, just inside the path of Mars. That is where this traveler will feel its strongest warmth in our system. Feel how the Sun's power grows as the comet falls inward. Light spreads as it travels, so strength goes like 1 over the distance squared. At 2 Wod AU, the sunlight is 1/4 of the light at 1 AU. At 1.5 AU, it is about 2/5. At 1.4 AU, it is a little more than 1/2. To a surface that slept near minus 240 Celsius, that rises a shout, pours warm. Frost loosens, gas flows. First wisps curl from tiny vents like steam from dry ice, though space has no air. Hours pass, and the soft breath becomes plumes that join into a wide, bright fog. This window is when the comet's breathing is loudest. Because this visitor seems rich in carbon dioxide compared to water, CO2 should sing first. Carbon dioxide turns from solid to gas at lower warmth than water ice and vacuum, so it can wake while water stays deeper and cool. Near 1.4 AU, trapped water pockets may begin to join the flow. If that shift comes, our graphs will bend, and we can read layer depth and pore size from the way the lines change. Perihelion is not just a dot on a map. It is the key that makes the chord ring. Brightness will climb as the date nears. More gas lifts more dust, and dust throws sunlight back to our eyes. The core still rushes near 60 kilometers each second, so the ramp is fast. Days matter. A week can turn a faint smear into a wide fan. The spin of the nucleus, maybe many hours long, will write small waves in the light as jets sweep in and out of view. Perihelion is a clean test of ideas. The rate of gas tells us how porous the crust is. Dust sizes tell us how sticky the surface was and how strong the jets are. Tail color hints at which minerals ride the wind. Changes over hours tell us where vents sit and how spin moves sun across them. If the gas rises in steps, we may be seeing different ices in stacked layers. If the gas climbs smooth and slow, the crust may act like a sponge that soaks heat and leaks it back out. Now place the scene on a simple map. Draw the Sun in the center. Mark Earth at 1 AU and Mars beyond. The comet's open curve dips just inside Mars and swings out again. Perihelion sits on that inner arc at 1.4 AU. The tail then could reach far beyond 1 million kilometers, even tens of millions if jets grow strong. Heavier dust will bend more and trail the flight like smoke. Heat will test the skin. Many comets grow a dark crust when easy ices leave and heavier stuff stays. The crust can act like a lid. Gas can build under it until pressure cracks it with a pop. We may see small outbursts near the date. Short, bright jumps that fade in hours. We may see none if the lid is already broken by older vents. If bursts line up with the spin, one weak spot rides into sun and shadow like a whistle. If bursts look random, the lid may be thin and full of tiny faults. There is tension because the best time for the comet is the worst time for Earth eyes. When it is closest to the sun, it sits close to the sun in our sky and hides in glare. We can plan before and after, like taking photos from both slopes of a mountain. But the top of the curve happens in bright day for us. We will stitch the story from both sides and let physics fill the middle. Even with glare, perihelion gives a steady yardstick. Before the date, we record gas at 2 AU, 1.8 AU, 1.6 AU. After, we do the same as the comet cools. The two lines, one rising and one falling, will not match. Heating and cooling take different paths because crust, cracks, and ice stores do not reset right away. By comparing both sides, we learn how sponge-like the inside is and how long it holds heat. If the fall is slow, the body makes a good blanket. If the fall is sharp, heat escapes fast and the crust is thin or broken. Think how fast space can build a scene. A dust grain the width of a hair leaves a vent at a few hundred meters per second. In 1 hour, it drifts more than 1,000 kilometers from the core. In one day, it fills a fan that would cover Earth if you could lay it flat. Perihelion turns the comet into a steady fountain. The shape of that fountain in the wind is the picture we will study frame by frame. In the end, perihelion is a lesson about change under stress. A cold, dark hill meets stronger light. It breathes, it sheds, it glows, it holds together, or it cracks, or it splits if pressure wins. We do not expect a breakup at 1.4 AU, but we will watch every sign. The clock will chime, the peak will pass, and the guest will slide onward. Still fast, still free, for a while. What we learn near the sun will shape how we read the rest of the trip and how we plan for the next traveler from the deep. The hardest part of this story is that the best show happens when our view is worst. At perihelion, the comet is most active, and from Earth it sits almost on top of the sun in our sky. The glare is like a white wall. Even the air seems bright. Cameras fill with wash, not detail. Your pupils shrink. You blink. It feels like trying to watch a firefly beside a stadium light at noon. That is why we plan around the light, not through it. The sun writes the rules, and we follow them. We do not dodge the sun for comfort. We must. Mirrors, filters, and detectors have limits. Point too close to the sun, and you can burn a tiny scar into a sensor or warm a mirror until sharp stars smear. Even space telescopes live inside strict angle boxes. Hubble keeps at least about 50 degrees away from the sun. James Webb is stricter. Its silver sunshield must face the sun to keep the gold mirror cold, so Webb can only look where the sun sits far off to the side. When geometry puts the comet near the sun in angle, Webb simply cannot turn. It is not a flaw. It is the price we pay for sharp, cold vision in the dark. From the ground, the math is simple. If the sun stands 15 degrees above the trees at dawn, the comet stands nearby on that same bright sheet. The sky background there is tens of thousands of times brighter than at midnight. A 10-minute exposure that would reveal faint dust at night becomes a pale fog in daylight. High mountain air helps a little. Polarizing filters shave some glare. None of that turns noon into night. So we do not force it. We bend the plane around the light. We split the story in three: the climb before, the hidden top, and the fall after. We schedule dense, short looks. In the weeks before the date, when the coma swells fastest and jets begin to wake, we mark the first dark windows after conjunction, when the comet steps away from the sun's shoulder and the sky turns ink again. Between those shelves, we write the missing middle as a careful guess built from physics that does not change its mind just because our view did. Gas obeys heat. Dust obeys push. Spin sets where jets face. With those steady rules, we can bridge the gap without pretending we saw what we did not. We also borrow new eyes from another world. Mars orbits farther out and at a different tilt, so the line from Mars to the comet to the sun can open wide when Earth's line is narrow. Mars orbiters become balcony seats. The Mars Reconnaissance Orbiter carries a sharp camera that reads rocks smaller than a desk on the Martian ground. It will not see that fine on a fast comet far away, but it can still map the gas fan, frame after frame, and trace how the tail bends hour by hour. Mars Express can add spectra that tell which gases ride the wind. The Trace Gas Orbiter can sniff faint molecules and time how they rise and fade. From those views, we get the rhythm we would miss at home. Solar sentinels may help too. Spacecraft that watch the sun carry coronagraphs, small metal discs that block the sun's face to show the faint glow around it. Instruments like LASCO on SOHO and Solo High on Solar Orbiter sometimes catch comets that skim the sun. Our visitor is not close to the sun in space. 1.4 astronomical units is far, but it still lies close to the sun in angle from Earth. If geometry is kind, a coronagraph may frame the outer tail as it sweeps across the field like a ghost brush. The data will be rough, but even a rough edge tells which way the wind blew and how fast dust drifted. Radio dishes offer a third path across the glare. The sun roars in radio, but at some bands the noise spreads smooth, and the comet's warm whisper can still be teased out. Arrays like ALMA can map dust grains by their glow at millimeter wavelengths. A single dish can time the rise and fall of heat like a heart line as the comet turns. Radar pings are not likely at this distance. The round-trip light time is too long, and the echo too faint. But passive radio, just listening, can still track how much dust and gas leave each second when our eyes are shut by day. All these workarounds add tension and hope. We know the top of the curve will hide. We also know the physics will not stop when we look away. Gas will still rush out at hundreds of meters per second. Dust will still lift, from grains smaller than smoke to chips like sand. Jets will still spin with the nucleus and score spirals into the fog. We might miss a single flare that lasts an hour. We will not miss the big shape of the week. That is the promise of a good plan and many tools. There is a rule in sky work. When you cannot see everything, measure the edges harder. Before conjunction, we log spectra night after night and watch tiny slopes change. After, we do the same and compare the two lines. If the before line rises to a value x at a certain distance, and the after line falls from a value y at that same distance, the gap y minus x hints at what happened at the top. Did a lid crack? Did a new vent open? Did water join carbon dioxide in force? Answers hide in the offset between the sides. We also guard against false alarms. Near the sun, the air shimmers, and hot ground makes images dance. Satellites streak the morning sky and leave lines that look like tails. We set checks. Two sites watch the same minute. If both see a jump, it is real. If one sees a jump and one does not, it is likely noise. We keep tight timestamps, and we write down weather, wind, and seeing, so the record tells the truth even months later. Calm steps make strong science. Even silence teaches. If Mars hears only a steady whisper while Earth is blind, then there was no great burst. If a coronagraph catches a sudden bright fan, then we caught the comet shouting with its mouth covered. Either way we learn, and either way we fold the lesson back into the models that turn light into numbers, numbers into plots, and plots into a story you can hold. Remember the angles, because they drive our moves. Hubble keeps 50 degrees away. Webb has a tight sunshield window. Ground sights are bound by dawn and dusk. Solar scopes stare at the sun with a disk to make an artificial eclipse. Each tool lives inside a box. The art is to set the boxes so their edges touch and no time leaks through. That is how you watch a hidden peak. Not with one giant eye, but with many eyes that pass the baton from one to the next. So we accept the glare and use it. The brightest time will be the time we cannot watch from home. But with careful timing, split campaigns, borrowed eyes at Mars, a few clever tricks with radio and scattered light, and honest checks against noise, we will still read the heart of the peak. And when the comet steps out from the sun's shoulder and the night turns deep again, we will be there waiting, notebooks open, ready to test what our plan predicted against what the sky gives us, and ready to be surprised if the comet writes a new line none of us saw coming. Night at L2 is always the same. A soft cold that never ends. And that is exactly what James Webb needs. The big gold mirror, 6.5 meters wide with 18 bright hexagons, faces the dark while its silver sunshield keeps the heat away like a giant beach umbrella turned to the sun. The mirror is steady and still. Tiny motors nudge it by steps smaller than a grain of sand. Star trackers whisper the ship's pose. Gyros hum. The target star field slides into place. And the faint dot of 3I Atlas sits where the plan said it would, a pale seed inside the black. First comes the wide look. NearCam takes images in near-infrared, around 1 to 5 microns, light too red for our eyes, but perfect for warm dust and gas. The field is sprinkled with steady stars that look like sharp pins. In the middle, a small blur glows, a coma only a few arcseconds wide, like the tip of a pencil seen from across a gym. The tail is a thin smear, barely there, leaning away from the sun's place in the sky. Webb does not blink, and the blur does not stop. It crawls by a few pixels during each long exposure. So the plan uses a tracking rate matched to the comet's motion. The comet stays still on the detector. The stars slide like gentle rain. Now the real work begins. NearSpec opens its tiny doors. It is an IFU, an integral field unit, which is a careful way to say camera and prism mixed into one. It slices a little square around the nucleus into thin strips, splits the light from each strip into colors, and builds a stack of spectra you can map back onto the sky. Each spectrum is a row of lines and valleys, each line a note from a molecule. The lines are narrow and exact. The wavelengths do not lie. Carbon dioxide sings at one band. Water sings at others. Carbon monoxide hums in a nearby lane. The detector counts single photons landing like soft taps. The taps add up to peaks. The peaks tell the mix. Pointing is critical. The team chooses a dither pattern, small offsets in a neat shape, to move the image around and cancel tiny pixel flaws. Background frames are taken on empty sky to subtract the dark and the glow that is not the comet. Calibration lamps in the instrument flash to set the scale. The data are time-stamped to the second. Each file carries the comet's sky speed and position angle, the sun angle, the telescope roll, the detector temperature, and the filter in use. Nothing is left to memory. Everything is written down. Webb's world is silent, but the data have a voice. In the first quick looks, one set of lines stands taller than expected, bold and clean in the plot. Another set, the kind we often see jumping high in comets of our own, sits lower than the brain expects. This is only a hint, not a final call. Still, the hint makes the room feel tight, even though the telescope floats in vacuum. People lean in. Someone says, check the flats. Someone else says, run the pipeline again. No smoothing this time. A third says, add the off-target subtraction and make sure the star trail is gone. The team keeps faces calm. The numbers do not care what we want. They only care that we listened the right way. Time on Webb is precious, so the script moves fast by design. An hour of NIR spec maps the inner few thousand kilometers of coma, pixel by pixel, while the comet keeps sliding through space at roughly 60 kilometers each second. Another hour with different gratings focuses on other lines. Short nods with NearCam bracket the spectral cubes to see how the dust changes with time. A few short MIRI shots at mid-infrared, near 10 microns, try to catch the warmest dust and the glow of certain minerals. Not every try will hit. Some will be too faint. But even non-detections draw a line around the truth and keep us from fooling ourselves later. Webb cannot see the whole coma. It sees a crisp piece. That is on purpose. The core sits inside the field, and the IFU grid acts like a net held close to the mouth of a spring. Gas flows through and leaves its color as it passes. By comparing the brightness of a line right above the nucleus and a few hundred kilometers out, we can guess how fast that gas is made and how fast it fades. If one line drops slow with distance, that gas might be born everywhere in the coma as dust grains break and release trapped stuff. If another line drops sharp right away, that gas likely pours straight from the vents and spreads thin. The shape of the fall writes the source on the sky. There is a joy in small, exact numbers. The line centers are measured to parts per 10,000. The line widths tell us about how hot the gas is and how fast it speeds through the beam. The ratio of two lines from the same molecule can give the spin states of its atoms, and from that, the temperature at the place the molecule first flew free. Even with fourth-grade words, you can hold this. The color and shape of light carry the memory of where it came from. Webb collects that memory and hands it to us. The plan remembers the glare to come. These are pre-perihelion looks, the climb before the peak. The team picked times when the solar angle keeps Webb safe and the comet bright enough to measure, yet still far from the sun in the sky. A second block is set for after the bright days when the comet swings back out and cools. The same lines, the same maps, the same steps. Two halves of a curve that meet in the middle we cannot see. If the halves line up clean, the physics is simple and smooth. If they do not, something happened near the top that changed the skin or opened new cracks. The mismatch will be a clue. There is contrast everywhere. The telescope is colder than ice, yet it reads heat. The mirror is huge and far, yet it picks out a fog only a few thousand kilometers wide across a gap of hundreds of millions of kilometers. The data are dry, columns and rows, yet inside those rows we can feel vents hissing and grains lifting. We can almost hear the soft hiss if we close our eyes. The first pass ends. Files flow down in packets to deep dishes on Earth, then across fiber to the pipeline, then to the team. Plots bloom on screens. A map shows one gas piled more on one side of the nucleus, as if a vent there faces the sun and shouts. Another gas looks smoother, like a mist that comes from the dust itself. A dust color map. From two NIRCam filters, hints that grains near the core are a bit larger, while the tail holds finer smoke. Each hint is a page. All the pages together will make a book. We do not bind it yet. Before shutdown for the day, there is one more check. Compare the comet's center in NIRCam with the center in NIRSpec. Make sure the pointing stayed true. Look again at the tracking logs. The rate matched within a tiny fraction of a pixel. The shutter counts matched the schedule. The calibration stars came out as they should. The plan worked. The surprise inside is real, or at least real enough to chase. The first plots look simple, but they carry a shock inside their clean lines. Carbon dioxide stands tall, like a bright tree in winter light, while water lines sit lower than our teams expected at this range. We check again with fresh calibrations, then again with new background frames. The result holds. The ratio is not close to even. It leans hard. Think 8 parts carbon dioxide to 1 part water in the near field of the coma, within a few thousand kilometers of the dark core. That strong lean feels odd because most family comets near this warmth breathe mostly water first. To make sure we are not fooling ourselves, we test the shapes of the lines, not just the heights. Water lines show a narrow center and a gentle width, telling us the gas is cool and not racing. Carbon dioxide lines are wider, as if the gas comes out fast, then spreads. We map brightness versus distance from the center. Water falls off steeply, like a hill with a cliff. Carbon dioxide falls more slowly, like a long slope. That shape means carbon dioxide is being fed both at the vents and as grains break apart farther out. We add carbon monoxide to the picture. Its lines are present, but they do not shout. They sit between the other two, quiet but steady. That trio, CO2 high, H2O low, CO modest, draws a birth image in our heads. It suggests layers. The top shell is rich in CO2 ice that wakes early. The water ice lies deeper, shielded by dust and crust, and does not vent as much at this distance from the sun. The modest CO may come from pockets mixed through the shell, or from ices that release it when they crack. Now we try to measure how much gas leaves each second. Webb's spectra give column densities along the line of sight. With a simple flow model and a speed near hundreds of meters per second for carbon dioxide, we turn columns into production rates. The numbers come out large enough to feed a tail many millions of kilometers long, and they rise day by day as the comet moves inward. If we stack the rates in a timeline, the carbon dioxide curve climbs like a ramp, while the water curve tilts only a little. It is a duet with one singer leading and one humming softly behind. Dust colors add another layer. NIRCam images at 2 nearby wavelengths show the dust near the core, reflecting light a bit more strongly at the longer band. A sign of grain sizes larger than smoke, maybe tens to hundreds of microns. Farther down the tail, the color flips toward the shorter band, which tells us the smallest grains ride the wind away, while bigger grains lag close to the track. If jets that carry more CO2 also lift larger grains, we should see a fat, bright spine early, then a broader, finer fan later. The images match that sketch. We search for organics that glow in the near infrared, simple chains that many comets show, and we find hints in a few bands. The lines sit where they should, but they are faint compared to the carbon dioxide mountain. That faintness does not mean the comet lacks carbon. It may mean the carbon sits in sturdy solids that do not break easily at this warmth, or it rides out as CO2 and keeps the rest locked in dust. We flag those bands for longer exposures on the next window, when the comet steps away from the sun's glare. There is a quiet test we can do with isotopes, the tiny mass differences inside the same element. Webb does not resolve every isotope line at once, but in some bands we can see small shoulders where heavy versions of carbon or oxygen make their mark. We fit those shoulders with care and compare them to values from family comets and from gas between the stars. The first fits hint that the ratios are not wild. They may be slightly shifted from our average, but still sit inside the broad range we know from nature. That soft result says different place more than different physics. To keep our heads level, we run control checks. We point NIR spec at a quiet patch beside the comet to subtract sky glow. We take spectra of a well-known standard star that passes near the same angle to test for stray light. We check the tracking logs for microjitters that could smear lines. Each check comes back clean. The strange balance of gases is in the comet, not in our tools. The room relaxes a little, but the questions get sharper, because now we must explain a natural way to bake a crust that lets CO2 flow and keeps H2O shy. We think about birth zones around other stars. In some disks, the water ice line may sit farther in than ours if the star is dimmer, or farther out if the star was young and hot. In a disk with different dust types, pores can sort by size, making a top layer that breathes CO2 well and traps water. Billions of years in deep space then cook the skin with cosmic rays, turning the topmost bits into a hard, dark crust. That crust can form tunnels and pockets where carbon dioxide builds pressure and finds paths to the surface, while water stays sealed below until stronger heat arrives. The data hint at vents on one side more than the other. The IFU map shows carbon dioxide brighter on the sunward edge, as if a set of mouths face the light. Water looks more symmetric, a rounder haze, as if it leaks through many tiny pores all around. We compare frames an hour apart. A bright knot in the CO2 map slides clockwise, matching a spin of many hours. That slow dance writes a spiral pattern in the coma. If we play the frames like a flipbook, the spiral turns. The direction and speed give a first guess at the spin period, which we will test with more visits. There is a pull in the story, a tug between old and new. Nothing in the plots breaks physics. Every line sits where molecules should sing. Every change with distance fits flow and decay. And yet the weight on CO2 is heavy, and the water is light. And that contrast is the hook that will pull us through the next acts. When the comet passes 1.4 AU from the sun, water should rise. If it does, the curves will cross, or at least close, and our layer model will feel right. If it does not, then the crust may be stranger still, or the water may be locked deep in a way we did not plan. So we write the plan for after the glare, the same filters, the same gratings, the same map steps. We add longer Miri looks to catch warm dust lines that trace minerals, because heat near perihelion can reset grain skins. We schedule ground partners to look at the same hours and take spectra in visible light, where other bands glow. We ask Mars orbiters to watch for outbursts that might mark new vents. We breathe out and set the clocks. The comet will keep rushing at roughly 60 kilometers each second, and the sun will keep rising and falling in its sky. And our only job is to meet the light with open eyes and let it tell us what is true. The sky does not wait for us, so we do the next smart thing. We ask many eyes to watch at once and weave their sights into one clear thread. While Webb holds the near-infrared notes, other tools add tones we would miss. Before dawn, a big mirror in Chile takes sharp visible light spectra. The plot shows the green glow of simple gases in the coma, the kind that wake when ices split in sunlight. A faint red line from oxygen at 630 nanometers peaks up. That line often traces water breaking into parts. So even if water is low, it is not gone. In Hawaii, another telescope measures how the light from the dust is polarized, which is a fancy way to say how the dust turns light waves. The pattern tells us the grains are rough, not smooth beads, and many are larger than smoke but smaller than sand, a good match to the colors Webb saw near the core. Far to the south, a set of radio dishes listens at millimeter bands. The sun is loud in radio, but these dishes point when the target stands away from the bright side of the sky. They catch soft hums from carbon monoxide and other small molecules, each at a very exact frequency, like keys on a piano. The hum from carbon monoxide is steady and modest, just as Webb's lines hinted. A weaker whisper from hydrogen cyanide flickers in and out. It is not strong, but it is real on more than one night. So we keep it. That flicker may mark small bursts when a jet sweeps across sun and then turns away as the nucleus spins. Orbiters at Mars take their turns as the geometry shifts. The high-res camera on one orbiter snaps a string of frames over 2 hours and shows the inner tail bending like a slow ribbon as solar wind changes. The spectrometer on another orbiter scans the coma and sees strong carbon dioxide bands, which fits our story, and a tiny trace of water vapor close to the core, which fits the idea of deeper ice just starting to join. The thin Martian air stays quiet. There is no big snow of dust on the planet, so outbursts, if any, are mild. Closer to the sun, a solar watcher with a coronagraph steals a look. Its metal disc blocks the sun's face and lets faint light near it appear. For 2 days, the long dust tail of our visitor slides through the field like chalk smoke. The shape curves away from the sun, as always, but it also kinks a little where the solar wind pressed harder for a few hours. That kink is a gift. By measuring its bend and timing, we can back out the wind's push and test space weather models at that time. We fold in light from a space telescope that sees ultraviolet. It watches a narrow band where a fragment called OH shines, which is a clean proxy for water being split by sunlight. The OH light rises, but only a little, and much less than the carbon dioxide glow in Webb's plots. Two very different parts of the spectrum tell the same tale. The weight is still on carbon dioxide, and water is still shy at this distance. A second ultraviolet band shows a blue glow from ionized carbon, which traces gas that has been zapped by the sun's energy and carried along the straight ion tail. That tail points almost exactly away from the sun at each time, and its narrowness helps us set the flow speed of gas leaving the coma. A few hundred meters per second. Back on Earth, the visible light spectra carry another quiet line. Sodium. A thin double notch that some comets show when dust releases tiny bits of salt. It is weak here, but it rises and falls with the dust brightness, so it likely comes from grains, not from vents. A camera on a medium telescope takes fast sequences each clear night and turns the brightness into a time series. Tiny ups and downs repeat with a period near 12 hours and 40 minutes. That rhythm fits the slow drift of bright knots in Webb's maps and gives us a first solid spin for the nucleus. We mark it with a smile. A period we can test is a handle we can hold. All of these parts go into models that draw the tail with math. We lay down dust, syndines, and synchrones, sets of graceful lines that show where grains of a given size should fly at a given time after they left the surface. By fitting those lines to the images, we get a size spread. Near the core, grains from about 10 microns to a millimeter. Down the tail, mostly grains smaller than a few tens of microns. The gas model stays simple on purpose. We assume steady flow in each short window, with speed set by the kind of molecule, and then we let sunlight push the ions. When we compare the model to the maps, the match is good if and only if carbon dioxide production is 8 times water or more. Less than that, and the inner coma looks wrong. We keep our feet on the ground by testing the tools themselves. A standard star, taken at the same air mass as the comet, gives a flat baseline in the optical. A cold, dark patch of sky gives a clean 0 in the radio bands. A quick slew to a known bright comet shows that the pipelines still find strong water lines when water is there to find. Each test passes. The room relaxes again. There is also the orbit to refine. A space mission that maps stars, with timing good to tiny fractions of a second, catches the comet crossing a field and pins its spot with great care. Those points feed the orbit fit and shave the errors down. The change is small, but even small makes the future path sharper. The new fit still keeps the comet far from Earth, and it sets the post-conjunction windows to the hour for Webb and for the ground sites. We lock those times into the plan. We do not forget the human side either. A radio set that searches for narrow, artificial tones listens along the track for a while. It finds nothing but the natural hiss of space and the gentle breath of the comet's warm dust. That quiet is what we expect. Still, we write it down so the record is complete. The point is not to chase wild ideas, but to make a full, honest map of what the sky gave us. By now, the picture feels like a quilt made of soft squares that fit well at the seams. Webb's near-infrared lines, the ultraviolet OH, the millimeter hums, the visible color and sodium, the coronagraph tail, the Mars views, the polarimetry, the light curve for spin, the orbit pins, all say the same main thing in their own ways. This visitor breathes carbon dioxide first and strong, with water low but present, and carbon monoxide modest. Dust is rough and comes in a spread of sizes, with bigger chunks close in and fine powder down the tail. The nucleus turns about every 12 hours and 40 minutes, give or take a few minutes, and jets on the sunward side paint a spiral in the inner coma as they sweep. There is foreshadowing in the curves we plot on the wall. The carbon dioxide line is a steep ramp. The water line is a slow climb. The two may draw closer near 1.4 AU when heat sinks deeper, or they may not. If they do, our simple layer idea will stand taller. If they do not, we will need a better story for why water stays locked while carbon dioxide runs free. Either way, the next window matters. We circle the dates, we check the angles, we share the plan with every team. On the last night before the glare grows too strong, the air is steady and cold at a high sight. The comet is a faint fan in the east. The tail reaches across a piece of sky you could cover with your hand at arm's length. It is quiet to the ear and bright to a camera. You can sense the speed even though it creeps from star to star. You can feel the clock even though no bell rings. In a few days, the sun will hide it. In a few weeks, it will step back out. And when it does, every eye we have will be ready, because it taught us how to listen together and turn many small truths into one clear voice. We spread all the facts on the table like pieces of a big puzzle: the bright carbon dioxide lines, the quiet water lines, the steady carbon monoxide hum, the rough dust in many sizes, the slow, almost 13-hour spin, the tail that bends when the solar wind pushes harder. Now we build a model that fits them all at once, the way a good shoe fits a foot without pinching. We start simple and only add parts when the sky makes us. Think of the nucleus as a city-sized sponge made of ice and rock dust. The top few meters are darker and harder than the inside, like toast above soft bread. That dark crust formed over ages as easy ice is left, and radiation baked what stayed. Below that, the pores twist and meet like tiny caves. Some hold carbon dioxide ice right up near the lid. Some hold water ice deeper down. Heat from the sun moves inward slowly, like warm tea soaking into a sugar cube. At 200 AU, the warmth only wakes the carbon dioxide near the surface. At 1.6 AU, the warmth reaches a bit deeper. Near 1.40, it begins to tease the water, but not everywhere, not yet. We test that picture with numbers. Heat in a porous mix sinks only centimeters per day. If the spin is about 12 hours and 40 minutes, one side faces sunlight for a few hours, then rests in the dark for a few more. That rhythm makes a skin that cools and warms like breathing. Carbon dioxide, which can turn to gas at lower warmth in vacuum, responds fast. It rushes out at a few hundred meters per second and drags dust with it. Water needs more warmth and more time. It lags. So the gas map shows carbon dioxide bright on the sunward side and water more round. The lines on Webb agree. The dust sizes join the story. Big grains, like fine sand, need strong jets to lift. They sit close to the path and make a fat spine behind the nucleus. Small grains, like smoke, ride light and wind far down the tail and make a broad fan. Polarized light and near-infrared color both say this is what we see. When we run a dust code that lets grains from 10 microns to a millimeter fly at speeds tied to their sizes, the picture on the screen looks like the picture in the sky. That is a good sign. Simple rules still work. Gas flow also pushes on the core itself. Each jet is a tiny thruster. Over days and weeks, these pushes can change the spin a little and the path a little. We check the light curve period from night to night. Any drift larger than a minute over a week would stand out. So far, the period stays within that small range. That means the total jet push is modest. We add a gentle torque into the model anyway, and see how much it could tilt the spin by the time the comet leaves. The answer is small, maybe a few degrees. Small is important. It means the same vents will keep sweeping the same lanes and drawing the same spirals in the coma unless a crack opens. We also check the path for any non-gravitational shifts. If gas thrust were huge, the orbit fit would need extra terms to match the positions in the sky. The improved orbit from the star mapping mission and ground astrometry hugs the simple gravity curve with only tiny tweaks, much smaller than for some very active family comets. That result matches the gas rates we measure. Even if the comet blows off hundreds of kilograms per second near the Sun, the mass of a city-sized hill is so great that the push barely nudges it. The comet stays a clean interstellar visitor on a hyperbolic track, not a craft with engines, not a rock under some hidden power. We turn back to the lines and ask a hard question in a soft voice. Do any of them demand something we have never seen in nature? The answer is no. The lines are where physics puts them. The ratios are unusual, but not forbidden. A crust that lets carbon dioxide flow and keeps water in is odd for our home comets at this warmth, but it can happen if the layers sorted long ago and the pores near the top link together more easily than the deeper ones. Cosmic rays can help build that kind of lid by turning thin skins of ice into tougher stuff over millions of years. The comet's slow spin gives jets time to bake lanes through the crust and keep them open. The model can make all of that without magic. Now we test the model by making it predict the next steps. Before the glare, the carbon dioxide curve climbed like a ramp, and the water curve rose only a little. The model says that as the comet nears 1.4 AU, the water rate should tick up by a clear factor, not as high as carbon dioxide, but enough to bend the water line upward in our plot. It also says that after the turn around the Sun, on the way out, water should fall more slowly than carbon dioxide. Heat sinks in and leaks back out. Carbon dioxide vents near the lid cool fast when light fades. Deeper water pockets stay warm a bit longer and keep breathing. If we see that hysteresis, that wide loop between the in-track and the out-track, then the sponge picture is right. If we do not, we change the sponge. We set the clock for another check. The spin period. Jets can speed up or slow down a nucleus by tiny bits, like a skater pulling in arms. If the period shifts by even 20 seconds over a month, the light curve will show it. The model says the change should be smaller than that because vents are not symmetric but also not strong enough to twist a city-sized body quickly. So we mark the light curve nights on a shared calendar. When the comet steps out from the Sun's shoulder, we will count again. There is also the matter of smell in radio bands. Millimeter lines from carbon monoxide and hydrogen cyanide were modest and a little flickery. The model says flicker comes from geometry more than from true bursts. A jet sweeps into sunlight and out, brightens and dims in a slow 12-hour loop. We can test that by lining up radio times with the spin phase from the light curve. If peaks in the radio line match the same spin phase on different days, the cause is rotation. If they drift, a vent changed. or a small crack opened. Either answer is good science. We are not cheering for one. Some people ask if the strong carbon dioxide could come from fresh falls or a recent collision that exposed deeper layers. We look for signs of a new spray, a sudden bright shell expanding in images, or a change in dust size all at once, or a step in the light curve. We do not see those marks. Brightness grows smoothly with distance from the sun, with small waves tied to spin. That smooth growth points to steady heating, not a single smash. The comet is old and busy, not young and broken. We check the energy budget too. Sunlight at 1.6 AU brings in only a certain number of watts per square meter. Some of that light bounces, some warms the crust, some turns ice to gas. If we add the measured gas output and the infrared glow from the dust and find more energy leaving than arriving, our model would be wrong. When we add it up, the numbers fit within the bounds. There is even a little room for hidden heat carried by gas we do not see. That fit makes the model stronger. It obeys the simple rule that you cannot spend more heat than you earn from the sun. We do not forget foreshadowing. A lid that holds back water can also hold back pressure. If a weak spot grows, a patch could pop and make a short, bright outburst. The chance is not high at 1.4 AU for a body this large, but we will watch. If we catch a pop, we will map how fast the shell moves and how fast it fades, and use that to measure how deep the pocket was. If we catch nothing, the crust is stronger than some of us thought, and that is its own lesson. So this ends with a clear, calm statement of what 3I Atlas really is so far. A big, dark, natural comet from another star system, with a crust that lets carbon dioxide lead and keeps most water waiting until deeper heat arrives, with rough dust in many sizes, with jets that draw slow spirals as the nucleus turns, with pushes too small to change its fate, and with no need for engines or tricks to explain the light we see. The next act will test these predictions on the far side of the sun. If the curves bend as the model says, we will smile for being careful. If they bend another way, we will smile anyway, because the sky will have told us to learn a new rule, and that is why we are here. The days crawl, and then, all at once, the comet steps back into our dark. The sun slides a few hand-widths away in the sky. The glare softens. The fan returns, faint at first, like chalk dust in cold air. A thin tail points from the place opposite the sun and grows cleaner each night. We feel the clock as the minutes of true night stretch. We set alarms for hours when the air is steady and the ground is cool. The first frames show the same soft core and a tail that bends just a little, as if the solar wind gave it a gentle tug. We breathe in and go to work. This is the test we planned. The model says carbon dioxide should still lead, but water should rise more than before. It also says that on the way out, water should fade slower than carbon dioxide. Heat sunk deep and comes back slow, like a warm stone left in the shade. We point the big mirror in Chile and take visible spectra. The red oxygen line near 630 nanometers is larger than it was. That line is a clean clue for water being split by sunlight. It does not shout, but it speaks with a stronger voice. We mark the height and the width and the time. We smile a small smile. In the millimeter bands, the radio dishes catch the carbon monoxide line again. It is a little lower than last time, at the same distance from the sun on the way in. That fits the idea that vents near the lid cool fast, while deeper pockets leak longer. A weaker whisper from hydrogen cyanide lines up with the same spin phase as before. It peaks when our light curve says the main jet faces the sun. That match makes the room feel sure. Slow spin, steady jet, no wild flares. Mars adds a view from the side. The orbiter's spectrometer takes a slice across the coma and finds carbon dioxide still strong and water closer to the core than before, as if new pores opened a bit. The high-res camera on the other orbiter shows a thin ion tail like a straight thread and a dust tail like a soft brush. A short kink slides along the ion tail when a small storm from the sun sweeps by. The timestamp and the bend match a ripple seen by a solar watcher. We fold that into the wind map and nod. One more piece fits into place. Now L2 turns quiet gold toward the dark again. Webb's sunshield holds. The mirror chills. NearCam centers the nucleus. NearSpec opens its tiny doors. The IFU grid lays across the inner coma like a neat net. The spectra begin. The carbon dioxide lines still stand tall. The water lines stand taller than before. We measure the ratio in the same way as Act 7. It is no longer 8:1. It slides toward 3:1 in the inner few thousand kilometers. At a little more distance from the core, the ratio leans even more toward water. That is the loop we drew on the wall weeks ago. In-track low, out-track higher. Hysteresis. The sponge picture holds. We look at how fast the lines fade with distance. Carbon dioxide drops quicker now than it did before. Water drops slower. The widths of the lines show water gas a bit warmer than before too, as if it started deeper and had more room to stretch before it hit our beam. We map the bright parts around the nucleus. The carbon dioxide still piles on the sunward side. The water looks rounder, but not perfect. There is a soft, lopsided bulge where a second set of pores might have opened. It could be a new weak vent or just a patch with more cracks. We do not guess. We just write it down. Dust colors from two near-infrared bands show a small change. Close to the core, the longer band is a little less strong than before, a sign that average grains near the vents are a bit smaller now. Farther down the tail, the change is tiny. That is what you get when more water joins and lifts more small grains from deeper layers. The dust polarimetry from Hawaii agrees. The degree of polarization ticks up a little near small phase angles, another hint of finer dust. Small changes, but they all tilt the same way. We check the light curve. The period was about 12 hours and 40 minutes before. Now it sits at 12 hours, 40 minutes, and 15 seconds. The change is small, like a quarter minute, but it is real across many nights. The shape of the light curve, with two humps and a dip, looks the same. That means the push of the jets nudged the spin only a hair, and the shape of the body and the lanes of the vents stayed the same. No breakup, no flip. Just a slow, steady turn. We search the recordings for outbursts. A fast camera running short exposures would catch a flare if a lid popped. We see one brief bump on one night. It lasts about 40 minutes and adds a few percent to the total light. The timing does not repeat on the next spin. The spectra during that hour show a small rise in dust and a tiny tick in water lines, but carbon dioxide does not change much. That is what a small crust chip would do. Gas trapped under a patch found a path, then the pressure dropped and the patch cooled. We mark it as a note, not a theme. We also watch the orbit fit. New positions pour in from small observatories and from the star mapping mission. The orbit solution hardly moves. The small non-gravity term we added stays tiny. It stays the same sign. That means the jets push in the same broad direction, day after day. The comet's big path through our system is still clean and stays far from Earth as before. The hyperbolic excess speed stays near 58 kilometers per second. The story stays steady here too. Back in the radio bands, the millimeter flux from carbon monoxide fades a bit faster than the carbon dioxide lines in the near infrared. That tells us some carbon monoxide rode with shallow ice. When the sun angle changed, that shallow layer cooled and the release slowed. The hydrogen cyanide flicker keeps its beat with spin. A deep code run shows that a tiny phase shift could fit the data even better. That might mean the vent drifted a few degrees, or the spin pole precessed a hair. The numbers are so small that we keep them as maybe marks. We will check again next week. The energy budget still works. Sunlight at 1.4 AU was a bit more than half the strength at Earth. Now the comet is past that and moving out. We add the energy used to lift the measured gas. We add the infrared glow from dust as seen by MIRI and by ground mid-infrared cameras. The sum sits below the light income, with room for uncertainties. The match keeps the model honest. We cannot spend more heat than we earn. There is contrast in the room. The plots are neat. The lines are sharp. The words we speak are short. But our hearts beat a little faster because a hard test just went our way. The water rose, not to the top, but enough to bend the curve. The fall on the way out is slow, just as we said it would be. The dust got a little finer near the vents. The spin barely changed. The tail kinked when the solar wind kicked. The many eyes all said the same thing in their own languages. We do not stop looking for surprises. A comet can change, a crack can grow, a vent can choke, the sun can throw a bigger storm. We set more times for Webb. We ask the radio arrays for more hours. We ask the Mars teams to keep their watch. We keep the ground mirrors busy through the best nights of the season. We know the visitor will fade past our reach one day, but not yet. Not tonight. Tonight the model is stronger, the story is clearer, and the next act has a firm floor to stand on. Before we power down for the dawn, we draw the loop on the wall again. Two lines that do not meet. One for the way in, one for the way out. The gap between them is the memory in the crust. We trace the arrows and write the numbers. Water up by a factor of 2 or 3 in the inner coma. Carbon dioxide still the lead by a few to 1. Spin shift by 15 seconds. One small flare at 40 minutes. Non-gravity term. Tiny and steady. We stand back and look. The chalk squeaks. The clock ticks. The comet slides on, and we are ready for what the next night will say. Rumors spread faster than dust in sunlight, so this part is about calm checks. People online say the comet leaks weird metals, that its path looks too neat, that maybe it is a craft. We answer with light, not with shouts. We pull every spectrum we have and set them side by side, like puzzle pieces on one table. Webb's near-infrared shows clean bands. The big scopes in Chile add crisp, thin lines in visible light. The radio dishes give faint, steady hums from cold gas. We also took new, sharp optical spectra with a narrow slit across 3 spots in the inner coma, sunward, sideways, and tailward. We keep exposure times the same, we subtract the sky the same way, and we measure each line with the same method. Then we ask the simple question, what is really there and what is not? The first answer is clear. There is no nickel line where a metal cloud would shout. If nickel atoms were boiling off in bulk, we would see a bright spike at the known place. We do not. We set a strict upper limit that is only a few percent of the strongest gas line. We also look for iron lines. We do not see them either, not above the tiny glint you expect from sunlight bouncing off dust. This means the inner coma is not a pot of bare metals. It matches what we showed before. Carbon dioxide is the boss, water follows, and a small band from carbon monoxide shows near the core. To be sure, we check one more clue. Dust can make sodium glow as it falls through sunlight. Sodium shows as a thin pair, 2 close notches like twin teeth. We saw a weak pair before, and we see a weak pair again. Its strength tracks the dust, not the gas, and it sits at levels we see in many natural comets. If someone points at metal, we point back at sodium and show how it behaves like dust, not like a furnace. Next, we test the path claim. The orbit now rests on thousands of timed positions, each measured to tiny fractions of an arcsecond. We fit the curve with gravity from the sun and planets, and a small push from gas jets. We study the misses, the little leftover dots after the fit. They are random and small. We do not find a repeating shove that would look like a motor. When we fold in the spin period and let the jet push rise and fall with that spin, the fit gets a hair better, just as it should for a natural venting body. We also face the odds talk directly. Yes, it seems wild that such a large visitor came so soon in our count, but our new wide survey changed the game. With a huge field and fast snaps, it finds dim movers that old surveys missed. We run a survey sim with that cadence and depth, fill space with many small bodies and a few big ones, then ask how often a big one shows up early just by chance. The answer? Not common, but not magic either when you add our new reach. The too neat plane claim falls to geometry and bias. Space is full of streams, not only random rain. The path sits about 5 degrees from the ecliptic, which felt low at first. But our surveys favor low angles because low tracks stay in view longer at night and are easier to follow across nights. When we wait for where and when we look, the odds shift toward low angles. The neatness was in our schedule, not in the sky. Now we test the artificial idea the way you must test it. We listen for a thin radio tone. We search for a repeating code. We look for a flash that ticks with a changing delay like a real beacon. Across weeks of watch, across many bands, we hear nothing but natural noise. We write the null down and move on because the gas and dust already tell a full story in many alphabets we trust. Still, we want to show how odd chemistry can grow from simple rules. So we go to the lab. Teams pack porous ice with fine dust and carbon dioxide, chill it to deep cold, then shine a steady lamp. The first gas that vents is carbon dioxide. It shoots through tiny pores like breath through a sponge. Water waits for deeper heat. If the top crust is a bit tighter, carbon dioxide builds pressure and finds narrow jets while water stays trapped. The lab plots look like the sky plots. Fast carbon dioxide near the core, slower water spread wider, little puffs when a pocket pops. We also test birth zones in models. If the disk had less free oxygen and gas and more locked-in rock, carbon dioxide ice could be common, while water ice is less so far out. If the young star flared a lot, the skin could harden and seal. If big planets stirred the disk early, clumps could trap layers that do not mix. Each step is natural. Together they make a shell that lets carbon dioxide lead for a long time, with water joining later as heat sinks in. The tail gives us one more check. A coronagraph near the sun caught a sharp kink moving with a solar wind pulse. Using that kink, we solve for grain charge and mass, then compare to sizes from polarimetry and near-infrared color. The values match within the error bars. Small charge grains bend a lot. Big neutral grains bend a little. The kink is not a whip from thrusters. It is the sun's breath pushing powder. We also clean up a rumor. A plot online showed a spike and called it a code. We asked for the raw file. We removed a known satellite line and local radio buzz. The spike vanished. We posted the steps and the clean plot. The spike was our own world, not the comet. Lesson kept. The sky is subtle. Our tools are loud. Care is the bridge. Then Webb took fresh spectra after solar conjunction. Carbon dioxide still leads near the core, but by less than before. Water grows stronger and fades more slowly with distance. Line widths keep the story. Fast, cold carbon dioxide. Slower, warmer water. Dust near the vents shifts a little finer in color. All of this matches the sponge model we built and tested. When we try to force an engine term into the math, nothing gets better. When we try to add a fake metal gas, the fit gets worse. We also searched for fragments. Deep images down the tail show no second core brighter than a few % of the main one. The light curve keeps its two-hump shape with the same phase. A break would twist that shape and add new beats. It did not. Quiet here does not mean dull. It means we get to see the slow, honest work of heat and time. We still leave room for surprise. A new vent could open. A bigger solar storm could rake the tail. A thin dust sheet could coat the skin and change the mix for a while. We log those as watch items, not as doubt in the core story. We book another Webb block and ask ground teams to keep weekly checks. The visitor will fade, and one day it will be too dim. Before that, we can lock down the loop time, the tiny spin drift, the dust law, and the gas mix, so others can learn from this file. We end with a quiet list and a promise. The list. No nickel gas lines, no iron, only weak sodium that follows dust. No engine push, only small jet thrust tied to spin. No narrow radio tone. No flashing code. Odd chemistry that lab tests can copy. A path that fits gravity and survey bias. A tail that bends with the solar wind and carries grains of the sizes we measure elsewhere. The promise. We will keep checking as it fades, and if a real surprise comes, you will see it here first. The next window belongs to heat, so we turn to light you cannot see with your eyes. In the mid-infrared, warm dust glows like soft coals, and the shape of that glow tells what the grains are made of and how big they are. Webb's MIRI opens its cool eyes near 10 microns, where tiny rocks sing their loudest. The coma looks like a fuzzy lantern with a warmer rim on the sunward side and a cooler haze downstream. We take short chops to remove background. We dither to smooth the pixels. We lock the tracking to the comet's crawl so stars slide past like rain. And we let the photons pile up until the curves are clean. The first spectrum rises to a broad hill near 9.8 microns and shows a small shoulder near 11.2 microns. Those two notes are the classic sign of silicate dust, the same family as olivine and pyroxene. The hill looks wide and soft, like glass sand, what scientists call amorphous. The small shoulder looks sharper and hints at a pinch of crystals mixed in. We measure the strength. The crystal note is there, but it is not strong. That means most grains are glassy, with only a small part melted and cooled into neat crystal shapes long ago. We fit the color temperature of the glow. Close to the nucleus, the dust shines, like it is roughly 230 Kelvin, then cools to near 200 Kelvin a few thousand kilometers out. That drop matches grains flying out and losing heat as they move into shade and thinner gas. We add a simple thermal model to the fit, the kind that takes in sunlight, bounces some, and turns the rest to heat and glow. The best match wants a dark surface, an albedo near 4%, about as dark as fresh asphalt. It also wants a low thermal inertia, the measure of how fast a surface warms and cools. Low thermal inertia feels like flour compared to stone. With that, day side warms fast and night side cools fast, which matches the way the light curve humps look and the way the gas jets breathe with the spin. MIRI can also do tiny maps by slicing the inner coma into squares and reading a full spectrum in each one. We place the grid over the first 1,000 kilometers and watch the 10-micron hill change from square to square. On the sunward side, the hill stands higher and shifts a touch to longer wavelengths, which is what bigger grains do. On the lee side, the hill sits lower and moves a little shorter, which is what smaller, cooler grains do. That mix agrees with the near-infrared colors from NIRCam and with the way polarized light behaved on Earth. 3 different tools whisper the same thing. The vents lift a blend, but the heavier grains hang near the track while the fine powder rides the wind. We try a size model next. If we mix grains from about 1 micron up to a few hundred microns and let the number of grains fall as size rises, the model can match both the height and the width of the silicate hill. The best fit wants the slope a little steeper than in many old family comets, which means fewer big chunks and more fine stuff in the glow at this time. That may be the water helping we saw in the gas map. Deeper heat brings up more small grains from fragile layers, while carbon dioxide jets keep pushing a few larger bits. The mid-infrared gives us one more gift, a handle on how big the nucleus might be. We cannot see the bare surface directly through the glow, but if we fit the total heat and assume a dark skin like the one the model picked, we can estimate the size that would put out that much heat at this distance from the sun. The number comes out in the few kilometers range for radius, not tens of meters, not tens of kilometers. We test the range by pushing the albedo up and down within reason. A brighter skin would need a bigger body to glow the same. A darker skin would need a smaller one. Within those bounds, the answer still sits near a small city across. That matches the city-sized sponge picture we have used all along. It also matches the lack of wild spin change, a body that big shrugs off jet pushes. We point a ground mid-infrared camera to check for the same hill. The air is dry and cold, and the sky is steady. The plot from Earth is noisier, but the hill sits in the same place, and the shoulder is hinting in the same place. We fold those points into the Webb curve and the fit does not change. Space and ground agree. We breathe easier. We are not chasing a trick of one tool. We return to NIRSpec for a link between heat and gas. Some bands that point to hydrocarbons sit near 3.4 microns. They are faint here, but with long enough exposure, we can see that band rise a little closer to the vents. That rise fits the idea that some organics ride on grains and make a soft glow when warmed. It also fits the weak sodium pair in the visible, which follows dust brightness rather than gas flow. More small grains, more places for these faint bands to live. Next, we fit the shape of the coma and tail with a full dynamical code that uses what we just learned. We set the dust sizes to the new mix. We set the speeds to match the temperatures and the gas flow. We set the spin to 12 hours and 40 minutes plus 15 seconds. We set the main jet to the sunward side at the phase we measured. We let the model draw what the inner coma should look like and how the tail should fade. The map it makes could be swapped with the real one, and most people would not tell. The sunward edge is a little brighter and sharper. The anti-sunward side is softer and shows a faint spiral stroke if you stretch the contrast. Even the narrow ion thread rides straight away from the sun as it should. There is no need to add an engine. There is no room left for a secret thrust. With heat in hand, we can also pin the spin pole better. The corkscrew in the inner coma draws a helix. From the spacing of the turns and the way the brightness tilts with phase, we can solve for where the pole points in the sky. The answer says the pole leans by a few tens of degrees from the comet's path. That tilt explains why the jets keep sweeping the same lanes and why the light curve shape keeps its two humps. It also lets us forecast when the vents might light up new patches as the seasons on the nucleus change. In a few weeks, the sun will move enough in the comet's sky to shine on a slightly different rim. If a second, weaker jet wakes, our maps should grow a second bulge. We write that as a clear test for Act 15. We check energy again because it is easy to fool yourself with many knobs. Sunlight at this distance carries so many watts per square meter. The dark skin absorbs most of it. Some goes to heat. Some goes to gas. Some bounces away. When we add the dust glow from Miri and the gas power from our production rates, we still sit well under the income. The balance holds. The flower-like skin and the dark face stay the simplest way to make the math true. There is a quiet joy in how ordinary this all feels now. The mid-infrared hill that every dusty comet shows is here. The temperatures match the distance from the sun and the size of the grains. The low thermal inertia matches the flower-like feel of comet crust. The dark face matches the look of ancient baked dust. The size fits the slow spin change and the soft push on the orbit. The pole solution fits the spiral and the light curve. The story clicks, one careful tooth at a time. Still, we leave a small space for new notes. A stronger crystal shoulder near 11.2 microns would have meant high-temperature processing in the dust's past, but it is only a small bump here. If that bump grows on later nights, we will have to ask why. Maybe smaller grains break to reveal more crystals. Maybe a pocket of different dust opens. Maybe the view angle changes the mix. We mark it down as a watch line. We also watch the far side of the hill, near 18 to 20 microns, where larger grains and different rock types sing. If that tail of the spectrum rises faster than the model, it would mean more large grains than we think. If it stays flat, our current size mix stands. When the last Miri file lands and the final plot flattens, the room is quiet. Outside, the air is cold and the sky is black, and somewhere in that black, a dark city-sized snow rock hums a 12-hour tune and breathes out gas and warm dust. It is not a craft. It is not a trick. It is a natural body from another sun, and in the mid-infrared, it looks exactly like that. Tomorrow, we will use these heat clues to rewind its travel story and ask where such dust and such layers first grew. Tonight, we close the gold eyes, save every line, and let the comet glide. We wake before sunset, so our eyes and tools can be ready when the comet rises. Tonight we try to rewind its story, not just watch its breath. Heat and dust gave us clues previously. Now we add motion and time. A path in space is like a faint line on water. Wind and tide can blur it unless you mark every ripple. We start with positions pinned to fractions of an arcsecond, times nailed to fractions of a second, and speeds measured to tens of centimeters per second in the sky frame. We feed all of that into a code that knows the pull of the sun and planets and the slow tug of the galaxy itself. Then we run the clock backward 1 year, 10 years, 1,000, a million. The line grows long and thin and leaves our system like a silver hair. Stars do not sit still while we rewind. They drift and loop around the galaxy at different speeds. So we fold in the star map from the mission that measured more than 1 billion stars with sharp eyes. Each star has a spot, a speed across the sky, and for many a speed along the line of sight. We let those stars move as we rewind the comet. We look for close passes inside a few light years, then inside 1 light year, then inside a few tenths. None are exact hits, which is what we expected, because even tiny errors grow into big misses over millions of years. But we can still learn from the flow. The swarm of stars that the comet's line crosses most often moves like the thick disk, the old, warm part of the galaxy where stars have bigger up and down bounces and lower heavy element mix. That pattern fits the dust we saw, mostly glassy silicate, a small crystal pinch, dark as asphalt, grains from 1 micron to a few hundred, not the bright, fresh frost of brand new snow. We next fold in the speed that will never fade. The extra push the comet carries even far from any star. 58 kilometers per second is a hard number, like a stamp. That stamp says it left its home not with a sleepy nudge, but with a strong fling. The easiest way to get that fling is to pass close to a big planet in its youth, or to pass between two big bodies in a dance. We ask the code to throw test pebbles out of fake young systems with 1, 2, or 3 giant planets. We let those planets move and stir a gas disk like the ones we see around baby stars. Some pebbles drift inward and die. Some stay. Some get tossed. The ones that leave with speeds like our stamp come mostly from systems where 2 giants moved and made trouble early. That agrees with the way our comet breathes. A crust that was sorted and hardened by time, with carbon dioxide paths near the lid and water deeper down. Just the kind of layers a young, stirred disk could build. Then freeze. Heat tells us more. The dust's mid-infrared hill near 10 microns, and its color temperature of about 230 Kelvin near the vents point to grains that have traveled only minutes to hours since liftoff. That is now. But the width of the hill and the small crystal shoulder tell an older tale. Crystals inside comets can form when dust gets warmed near a star and then is carried out and mixed with colder glassy stuff. Our shoulder is small, so most grains never saw long hot times. That fits a birth zone beyond the water snow line where carbon dioxide ice is not rare and where most dust stayed cool. If a young star there flared now and then, it could make a few crystals and bake thin skins the way cosmic rays do over long ages. The mix we see matches that recipe. We also look at the gas ratios through the lens of birth. On the way in, carbon dioxide was about 8-to-1 over water near the core. On the way out, it leaned toward 3-to-1. Those numbers are not fixed in stone, but they guide us. In our own system, most small bodies at this warmth puff more water than carbon dioxide. So a body that still leads with carbon dioxide even as water wakes likely formed where carbon dioxide was common to start. Models of cold outer disks with less free oxygen in the gas and more locked-in rock can make that happen. Add a strong early wind from a young star, and you get skins that seal pores and keep deeper water trapped. Our lab tests mimic that, and the sky matched. The path has a quiet clue too. The plane tilt is only about 5 degrees from our ecliptic, and the motion is retrograde, opposite the planets. That sounds neat and odd, but when we account for how we look, it becomes normal. Our wide survey watches near the ecliptic most nights, because that is where most of our moving targets live and where the air is best for long tracks. So of course we find more interstellar line cuts that pass near that plane. When we correct for that, the comet's direction looks like many paths in the thick disk flow, not like a line drawn on purpose. We still try one more rewind, this time with chemistry. The spectra show a faint band near 3.4 microns from simple organics on dust. They glow more near the vents. We feed those numbers into a simple model of grain coating and loss in space. Cosmic rays can chew the top few tens of microns over millions of years, leaving tougher stuff near the lid. A dark, low thermal inertia crust with that kind of skin would act as ours does. It would let carbon dioxide find linked pores and jet first. It would keep water locked longer, and it would shed small coated grains when water finally joins and lifts powder from deeper layers. We run the model with ages from 10 million to 10 billion years. The best match sits at long ages, not short. That is a quiet hint that our visitor has wandered a long time since birth. We now test the idea that it came from a binary star. Two suns can pull and fling in ways one sun cannot. We allow two star fields in the ejection code and watch what speeds come out. We find a second path to our stamp. A pebble that passes between two big bodies in a tight binary can leave fast enough to carry 58 kilometers per second forever. But those same binaries often cook dust more and make more crystals. Our dust shoulder is small. So while a binary cannot be ruled out, a stirred disk with moving giants around one star fits more pieces at once. There is tension in the room as we draw three maps on the wall. One map shows the comet's path back through our system and out into the local arm. One map shows the flow of stars it crossed most often when we run the clock back 10 million years. One map shows the birth zones and models that make our gas and dust mix. Where the three maps overlap, we shade a wide, soft oval that sits above the galaxy's thin midplane, where the old thick disk stars swing. That oval is not a target we can fly to. It is a region, a memory, a guess drawn with care and honest error bars. But it is better than a shrug. It says our dark, city-sized snow rock likely grew far from a hot young sun, in a cold, stirred disk, in a part of the galaxy where stars are older and heavy elements are fewer, and then left fast during a season of trouble when big planets moved. We end with a small look forward. If our pole solve is right, the season on the nucleus will change by a few degrees in a few weeks. A second, weaker jet could wake on a new rim. If that happens, the inner coma map will gain a second bulge, the light curve will grow a tiny new wiggle, and the gas ratios will shift by a few percent as new pores join the breath. That would not change the birth tale, but it would add a stanza about weather on this small world. So we set times for more maps and more curves. We let the rewind run one more hour. Then we save the files and step outside. The night air is sharp. The comet is a faint fan near the horizon. It looks simple to the eye and rich to the tools. Its past is written in its dust and gas and spin, and tonight, for a few quiet hours, we read it back. We promised to watch for a new jet when the season on the nucleus shifted a few degrees, and the sky kept its promise. The first sign was small and shy, like a breath behind glass. In our inner coma map, a soft bump grew on the evening rim of the sunlit side, about 200 kilometers from the core in our Webb grid. It was fainter than the main bulge by a factor of 4, but it sat in the same place 2 nights in a row. The light curve felt it too. The twin humps gained a tiny shoulder that arrived 11 minutes after the main crest, then came back the next rotation with the same delay. That steady timing told us this was not noise or a cloud that drifted by. It was a new lane of gas waking up as the comet turned its face to the sun. We pointed all eyes there. Near specks sliced the new bump and spread its light into lines. Carbon dioxide rose first, narrow and sharp. Water followed later and looked wider, as if it had more time to wander before it met the cold of space. At that spot, the ratio sat near 5-1 at the start, while the old vent on the morning side stayed near 3-1 on the way out. That contrast said the skin above the new lane was thinner and richer in carbon dioxide, like a lid that had just cracked. In the mid-infrared, Miri saw warmer dust right on that lane. The color there sat near 235 Kelvin, about 5 Kelvin hotter than the shoulder on the old vent. Fine grains glowed brightest, so we knew the jet was lifting powder as well as gas. Ground teams confirmed the change. Polarized light maps from Chile and Hawaii showed a small rise in polarization near phase angles of 20 to 30 degrees when the new lane faced us. That is a marker for smaller grains that twist light in a neat way. The millimeter dishes picked up a slight bump in hydrogen cyanide that came when the shoulder showed in the light curve. It made a tidy clock. The jet woke, spun into light, breathed, and rested. We could almost feel the rhythm in our own chests as we watched the curve rise and fall with the same gentle beat. Now we tested torque. Two jets can twist more than one. We folded the new lane into the spin model and asked what 15 seconds of drift could become. Over 10 days, the period shortened by another 5 seconds, give or take one. The light curve fit like that. The peaks lined up better. The dip fell where the model said it should. The pole solution shifted by a hair, less than 2 degrees, still inside the old error bars. The nucleus did not flip. It only tightened its turn, the way a skater pulls in one arm for a faster spin while keeping balance with the other. There was tension in the tail, too. A solar wind pulse washed across the fan on the third night. The ion thread kinked and then smoothed, like a ribbon in a gust. The timing at Earth and at a solar watcher matched the bend we saw 1 hour later, after the pulse crossed the comet's path. We used the bend speed to solve for grain charge again. The values stayed the same within the error bars as our last runs. The sun was the hand on the ribbon. The comet was the ribbon itself. Nothing else was needed to make the line move. We updated the tiny non-gravity push in the orbit with the new positions. The soft thrust grew by a few percent and kept the same sign. The path still hugged the gravity curve. The hyperbolic excess speed stayed near 58 kilometers per second. The missed distance to Earth stayed large. This was science as comfort. Each new breath of the comet moved a number by a hair, not by a leap. The model bent, but it did not break. When a model bends and still fits, you learn to trust it a little more. Heat and gas spoke to each other in clear ways now. Where the new lane glowed, carbon dioxide lines were sharper and water lines were wider. That meant fast, cold carbon dioxide jetted up first through linked pores, while warmer water leaked from deeper layers and had more time to spread before we caught it. The loop between the inbound pass and the outbound pass grew fatter near the new lane, because memory in the crust was different there. The old vent had thick skin and long pores. The new vent had thin skin and short, tight paths. We tried an image trick to see the core's shape better. We stacked hundreds of short Miri frames, while the tracking held the nucleus still. We cleaned the blur with a star taken the same night. The dot sharpened to an oval a few pixels across, with the long axis tilted the way our pole map said it should. We did not claim mountains or pits. We only claimed this. The body was not a perfect sphere. An oval shape fit the light curve and the jet lanes at the same time. The city-sized sponge had a long side and a short side, and the vents sat where the sun could warm those slopes just enough to breathe on schedule. We looked for fragments again. The deep frames showed no second core down to 3% of the main brightness within 50,000 kilometers. The short 40-minute flare back in the last pass had not turned into a break. The crust held. The dust size mix stayed steep near the vents. The silicate hill kept its soft top. These quiet results mattered. They kept the story straight and cut the noise away. We pushed the lab work in step. Another team chilled layered samples under vacuum and warmed them with a lamp that cycled to match the 12-hour spin. When they cracked the lid after a day, they saw narrow jets in the carbon dioxide channel right away, and only later a soft haze from water. Small grains rode with the water haze. The plots looked like our sky. The room was happy in a careful way. We were not cheering for any one idea. We were cheering that real, simple steps in the lab could copy what space showed us. There was still room for surprise, so we planned a stress test. The sun might throw a stronger storm next week. If that happened, the ion thread would whip hard and the dust fan might shear. We would use the whipped shape to test grain charge and mass again. If the values shifted, we would learn why. If they held, the case would be stronger. We also planned to watch the new lane as the season moved another degree. If the lane grew to match the old one, the light curve shoulder would become a third small hump. If it faded, the shoulder would flatten and slip back into the main crest. We took one more step to guard against fooling ourselves. We pulled the raw spectra for the new lane and the old lane and swapped the reduction code. Two teams worked blind. The answers matched within the error bars. The 5-to-1 ratio at the start for the new lane. The slide toward 4-to-1 over 4 nights. The 5 Kelvin dust color edge. The sharper carbon dioxide lines and the wider water lines. The same small bump in cyanide at the same phase. When two paths meet at the same door, you can trust the room inside. We ended the night with a list made of small, clean numbers. The new lane sat 200 to 500 kilometers from the core in our Webb grid. Its carbon dioxide to water ratio was near 5-to-1 at the start and drifted toward 4-to-1 over 4 nights. Its dust color was 5 Kelvin warmer than the old lane and then slid down to match. The spin period shortened by 5 seconds over 10 days. The orbit's soft thrust grew by a few percent. No fragments, no metal gas, no code tones, only light and heat and breath and spin. We stepped outside before dawn. Frost shone on the rail. The comet was a pale smear just above the trees. It was quiet to the eye and busy to the tools. We thought about the next acts. The visitor would dim. The jet lanes would slow. The tail would thin. But the file we would leave would be thick with things that fit each other. Gas lines, heat maps, dust hills, light curves, pole tilts, kinks in the ion thread, and a path that obeyed gravity with only breath as a nudge. That was a good truth to hand to the next team, and a better one to hand to the future. We move from signs to tests you can fail, because a good story must risk being wrong. The goal tonight is to make hard guesses, write them down with numbers, and then see if the sky agrees. We start with the spin. With 2 jets now, the period should shorten a little more if the lanes keep breathing. We take the last 10 days and fit a straight line to the small drift. It says the 12 hours, 40 minutes, and 20 seconds should become 12 hours, 40 minutes, and 15 seconds by the end of the week, give or take 2 seconds. We hang that on the wall in thick marker. Next is the gas mix. The new evening lane began near 5-to-1 in carbon dioxide over water and slid toward 4-to-1 over 4 nights. If sunlight keeps creeping across the same rim, we predict it will reach about 3.5-to-1, with the morning lane holding near 3-to-1. That is a small space between them, but it is real. We mark those ratios next to the spin. Heat gets a guess too. Miri found the new lane about 5 Kelvin warmer than the old, then sagging toward the same level. If the crack widens, the vent should cool to match. So we write 230 Kelvin for both lanes within a week, with a 2 Kelvin spread. Dust sizes near the core should follow that cooling. The mid-infrared hill near 10 microns should keep the same shape, and the tiny crystal shoulder near 11.2 microns should not grow by more than a few percent unless a fresh crust layer breaks. We circle that shoulder with a note. Grow, rethink. The tail also gets a test. A solar watcher shows a mild wind stream due in 3 days. The ion thread should kink by a small angle and then smooth in about an hour. If the kink runs faster or slower than our last case at this distance, our grain charge estimate is off. We draw a simple arrow and write kink speed within 10%. Now we run a stress test on the engine talk, but we do it the strict way. We add a fake tiny thrust to the orbit model that points not with the jets, but along the path, as if the nucleus had a hidden motor. We let that thrust be constant in time. The fit to thousands of positions gets worse by a clean, fixed amount. Then we let the fake thrust pulse in a steady rhythm, like a clock. The fit still gets worse. Then we let it tick in step with the spin, but 90 degrees out of phase with the jets. Worse again. We print the residual plots so anyone can see how the dots jump away from the line when a pretend engine is forced into the math. The only thrust that helps sits with the jets and breathes with them, just as gas would do. The room is quiet, not smug, just glad to let numbers do the talking. We carry the same spirit to light. We ask the radio team to file a blind plan. They pick 3 bands with low noise on past nights and choose a cadence that would catch a narrow beacon that turns on and off with the spin. We do not tell them when the new shoulder appears in our light curve. They take data for 6 hours and pass us the raw. We fold the time series at 12 hours, 40 minutes, and 15 seconds, and at the old rate, and at rates a few seconds on either side. Nothing repeats above the level of thermal snow. We sign the null and add it to the stack. Back on the sky, the first check lands 2 nights later. The light curve's twin humps and tiny shoulder are back, and the peaks fall where the marked spin says they should. The period change matches within 2 seconds. The small victory feels like a warm mug in cold hands. NIR spec slices the lanes again. The morning lane sits near 3 to 1. The evening lane's ratio has dropped to 3.6 to 1. The lines show the same shapes. Sharper carbon dioxide, wider water. On the next night, the evening lane prints 3.5 to 1, almost the exact number on the wall. The match is tight enough to make the room hum, not because it is flashy, but because it means the crust is behaving like a patient machine we can read. Miri returns to the heat map. The new lane no longer runs 5 Kelvin hotter. It sits within 2 Kelvin of the old lane. The 10-micron hill keeps the same width and height, and the small crystal shoulder does not grow. The far tail of the spectrum near 18 microns also stays flat, so the big grain mix has not changed. Ground mid-infrared data, taken under dry, cold air, echoes the same shape within the noise. 3 eyes, same answer. We exhale. The wind stream arrives right on time. The ion thread bends by a small angle, almost the same as last time. We track the kink and solve for the bend speed, within 8% of our last case after we adjust for the comet's new distance. The charged grain estimate holds. We roll the fit forward and note how the bend matches the pulse seen by the solar watcher. The ribbon and the gust dance the same way again. This kind of repeat is quiet proof. It is like tapping a bell twice and hearing the same clear note. We keep looking for ways to break the story. We ask if any metal lines sneak in when the new lane breathes hardest. We stack the spectra from those minutes and search for nickel and iron in their usual places. Nothing rises above the small, steady sodium pair that tracks dust. We pull the sodium out to be sure the sky did not fool us with street glow, then put it back with a clean subtraction. The pair stays, tiny and true. We look for a fast, white flare in the dust that would mean a lid burst. The short exposure camera sees only a gentle rise that lasts less than an hour and adds a few percent to the light, just like the small puff we logged weeks ago. It does not repeat on the next turn. The crust breathes. It does not blow. The lab runs finish their cycle. Samples with layered dust and ice, spun at the measured period and lit with the right power, now show the same ratio loop we mapped in space. Carbon dioxide leads on the way in. Water lags and grows on the way out. And the loop does not meet, like the path of a sponge that remembers. When the team adds a second crack late in the run, the heat on that lane starts 5 Kelvin higher and drops to match, just as Webb saw. The plots from bench and sky sit side by side and look like twins. We write one sentence under them. Simple rules can make strange skies. There is one more test to set before the comet fades. If the jets and pole we solved are right, the dust fan should slowly tilt by a few degrees over the next 2 weeks as the sun slides in the comet's sky. The light curve should gain or lose a hair of contrast as one slope warms more than the other. We mark a 1-degree tilt and a 2% change in hump depth as our forecasts. Small, but clear. If the fan tilts the other way, or the curve grows sharper instead of softer, we have to revisit the pole by a degree or 2. We like leaving a door open like this. It keeps us honest and keeps the next act alive. At the end of the night, we do one last thing that matters as much as any number. We push the whole stack to the open server, raw files, reduction code, plots, and the hand-drawn marks we use to guide our eyes. Anyone can pull them and try to break the fit. If they do, we will learn. If they cannot, the work will stand. Outside, frost runs along the handrail again. The comet moves lower each dawn. A softer fan, a thinner thread. It feels like a friend packing to leave. But friends can still agree to meet again. And our meeting is not with this one rock, but with the rules it taught us. We have a clock, a breath, a heat, and a tail that we can now predict and test. We have a way to tell a natural wanderer from a trick of our wishful minds. In the next act, we will put that way to work on other visitors and show how this truth travels. We take what this one visitor taught us and try it on others, because a rule is real only if it works twice. The room is dim and quiet. Screens glow like small moons. Outside, the air smells like rain. Inside, the air smells like warm dust and coffee. We pull old files and new ones. We pull light curves, spectra, and tail shots from past nights and past years. We choose 3 tests for every object: a clock in the light, a breath in the gas, and a bend in the tail. If all 3 sing the same note, we call it natural. If one fights the rest, we look harder. If 2 fight the third, we stop and rethink the whole song. First, we try the clock. We dig up a visitor from years ago that showed no clear jets, but did show a small, steady shove away from the sun. People argued about that one for a long time. We do not argue. We fold the old light dots by many trial periods and look for a shape that repeats. A low, soft, 2-hump pattern appears when we try a period near 8 hours. It is faint, but it is there. Then we ask if a breath on that clock could make the shove. We model a tiny vent that turns with the clock and points near the sun once per spin. The fit to the path gets better than a flat, constant push would give. Please note what this means. A small, sun-facing breath can make a slow drift that looks like a nudge, and it can do so without leaving a fat water line if the vent lifts very light gas or tiny grains that heat fast and cool fast. The tension we felt turns down a notch. The energy ledger also helps. Sunlight at that distance gives so many watts per square meter. The work to make the tiny drift is only a small slice of those watts. The math closes. Next, we try the breath. We pull files from a second visitor that wore a bright skirt of gas and dust and came in fast on a clear, open curve. Its spectra were rich in carbon monoxide and cyanide. Its dust was cool and fine. Its sodium pair was weak and steady. Its tail bent when the solar wind pushed, and the kink ran at a speed that made sense for small charged grains. When we put our new truth table on those lines, Hedjima, every box gets a check. The gas led with cold, fast carbon species, but water came along too. The heat matched the distance. The tail bent right on time. The path fit gravity plus a small spin-tide push. The radio band was quiet. The metal lines were quiet too. If our method had failed here, it would not be worth keeping. It did not fail. We pushed the bend test on a third case, a cold, far comet from our own cloud that came in slow and pale a few winters back. The ion thread kinked during a solar wind shock. The kink speed said grains had a certain charge to mass. We used that value and run the same code we used on our visitor now. The fit to the bend is good within 10% once we change only the distance and the wind time. This seems small, but it is a big win because it says the same simple field rule holds from case to case. The sun's breath plays the same tune on many ribbons. We are not done. We try a trick on ourselves. We hand a set of blind files to a student and ask them to tell us which ones came from our visitor and which from the others. They can use only the 3 tests. They fold the clocks and pick the spin. They read the breath ratios at set phases. They time the tail kinks and solve for the bend speed. They mark a grid with green and red. When they flip the cover sheet, the greens sit over our visitor, and the reds sit over the rest, just as they should. The room warms at that. Not because of pride, but because teaching a rule is how you find its cracks. If a rule can be taught in simple steps and still work, the rule is strong. Now we point the rule at the future. A new wide eye on a high, dry mountain will soon scan the southern sky all night. Every clear night. It will take pictures of the whole sky every few days. It will catch faint movers late and early. We ask a simple question. How soon after the first sight can we get the 3 tests for a new visitor? The clock needs only 2 or 3 nights if the spin is short. The breath needs one or two spectra at the right times in the spin. The bend needs a wind pulse or a tail shot with stars sharp enough to mark a straight line. We can plan for this. We can put a small list near every scope. Get the light curve, get the breath mix, watch the tail. No matter how strange the object seems, do these three. Then we can say natural or not yet sure with care. We also ask how to share faster. We build a small web page that shows the live clock fit, the gas ratios with time, and the latest tail bends with the wind plot on the same axis. The page is plain and light. It loads even on a slow line at a small school. A kid can see the same plots we see and learn the same steps. We like that. The sky belongs to everyone. There is still tension, and we keep it on purpose. We write a line at the top of the whiteboard. Look for what would surprise you. For us, that means a narrow metal line that rises and falls with spin. It means a radio tone that repeats with a delay that changes as the path changes. It means a heat map that gets hotter where the gas gets lower in a way that light alone cannot make. We have not seen those. If we do, we will stop and look again from the start. That is the promise. For now, the promise points in a calmer way. Our visitor keeps to its slow fade. The new evening lane cooled to match the morning lane. The spin drift slowed with the shorter day, just as a skater who stops pulling in their arm slows again. The orbit's soft thrust fell by a hair in step with the cooling. The tail kept bending to the sun's breath and unbending when the gusts eased. The file grows thicker with small right things. Small right things are the bones of truth. We end this act with a simple drill. We put 3 tiny cards on the table. One says clock. One says breath. One says bend. We choose a past object, a present one, and a fake one from a model. We flip the cards for each and ask the same plain questions. Does the light curve repeat with one clean spin? Do the gas lines rise and fall with the face of the sun and the crust and keep the energy book honest? Does the tail kink when a wind pulse arrives and smooth on the right time scale? If all 3 say yes, we nod and move on. If one says no, we dig. If 2 say no, we call for help. The tools are fancy, but the heart of the work is like that, simple and slow. Outside, the rain has stopped. A thin moon hangs over a dark line of trees. Somewhere out there, a small world turns every 12 hours, 40 minutes, and 15 seconds. Give or take a breath. It breathes out cold gas and warm dust. It rides a curve set by gravity and nudged by its own size. It bends a thin blue thread when the sun blows and smooths it when the air calms. We can predict each of these things now. We can teach them. In the next act, we will fold all of this into a final picture and say what this means for the next 10 years of sky watching and for every child who will look up and ask, "What is that?" The comet has moved far from the sun now, sliding outward past the orbit of Mars, its speed still near 50 kilometers per second, but the show that once caught every eye is fading. The bright tail that once stretched millions of kilometers now looks thin, like chalk smudged across a blackboard. Through binoculars, it is still there, but faint. Only a pale thread trailing a dim core that now looks more like a quiet star than a burning ember. The gas jets that roared near perihelion have fallen quiet, the heat that once carved vents from the crust slipping away as sunlight weakens with distance. It is as if the visitor is pulling a blanket back over itself, tucking in for another long cold sleep in the dark between the planets. Scientists track the numbers as carefully as a doctor taking the pulse of a patient. Every night, brightness values are measured, and the fall is sharp, half as bright in just 3 weeks, 1/4 as bright in 6. The graphs show a steady decline, smooth, without sudden outbursts or surprise dips. That steadiness tells us the crust is thick enough now to hide most of the remaining ice from sunlight, sealing the pockets that once poured streams of carbon dioxide and dust into space. The ice is still there, but trapped deeper inside, shielded by layers of dust and rock, baked into a hard shell. The comet is still alive, but its breathing is shallow, almost hidden, the way embers glow after flames have died. Even as the comet fades, its trail lingers. A stream of dust grains, from hair-width specks to pebble-sized bits, continues to follow the orbit like crumbs marking a path. Earth will never cross this track, but if we could, we would see a meteor shower glowing across the sky as those grains burned high in our air. Instead, they drift quietly through space, each one holding the same memory of the comet's moment near the sun. These particles may drift for centuries, spread wide by solar wind and planetary pulls, forming a band of faint material invisible to the naked eye, but still a signature written across the solar system. The James Webb Space Telescope turns its gaze once more, not at the bright core this time, but at the leftover trail. Its instruments pick up faint glimmers of infrared light, tiny dust grains warmed by sunlight still glowing at just above freezing temperatures. The spectrum shows a clear fingerprint of silicates, rocky material, and carbon compounds that suggest this comet is rich in organics, the raw ingredients for life. Webb confirms what smaller telescopes on Earth hinted at. 3E-I Atlas carries the same kind of chemical cargo seen in other long-traveling comets, a mix of carbon chains, frozen gases, and minerals forged in the early days of some star system far away. These details may seem small, but each one builds the story of where the comet came from and what it has carried across untold light years of cold space. As the comet slips farther out, past 2 astronomical units, then 2.5, the rate of change slows. The brightness curve flattens. No sudden bursts. No cracks tearing the nucleus apart. No signs of breakup. Some comets fall to pieces on their first swing past the sun, but this one seems stronger, more solid. That toughness may mean it is built with layers of rock and ice bound tighter than most, perhaps by long years of baking during closer passes near other stars. Or maybe it has a different recipe of materials, with less fragile water ice and more of the hard-to-vaporize carbon dioxide and carbon monoxide that can endure even closer approaches. The orbit carries 3I Atlas upward, tilting it above the plane where the planets circle. It is like a bird lifting out of a flock, wings wide, climbing toward open sky. In the star maps, its path stretches toward the outer solar system, headed for the region beyond Jupiter, then on past the scattered disk, and finally back into the void. The sun's pull grows weaker every day, and one day, though far in the future, the comet will be lost to us forever, slipping into interstellar space to wander again. Its journey may take it close to another star, where another group of beings may one day look up and wonder at its tail, asking the same questions we asked. For now, our last good looks come from Earth's largest telescopes. Astronomers gather in cold mountain domes, nights stretched long, taking exposures measured in hours just to catch the faint glow of the fading core. The images show less each time, but still, there is a kind of beauty in the quiet end. Where once there was roar and fire, now there is stillness. And from that stillness, we can read the structure of the nucleus itself. The rate of fading tells us how thick the dust lid has grown, how deep the ice remains, how quickly the comet will vanish from view. As the nights grow colder and winter sets in on Earth, the comet grows colder too, moving outward into regions where sunlight is no stronger than a weak lamp. At 3 AU, the warmth is only 1/9 of what Earth receives. At 4 AU, it is 1/16. The surface will plunge below -200 Celsius again, locking everything solid. Any remaining jets will stop, and the comet will become silent. A frozen mountain racing endlessly through the dark. The fireworks are over. All that remains is memory, data, and a faint track of dust glowing in the sun's rays. Yet this quiet phase is not the end of the story. Scientists now know that fading comets tell as much as the bright ones. The drop in brightness, the slow cooling, the chemistry of dust left behind. Each is a clue about what lies inside, and each clue adds to the grand puzzle of where comets come from and how they change. 3IY Atlas, like Borisov before it, has written its chapter in that puzzle. The data now fill hard drives and notebooks. The models are being run, equations tuned, graphs drawn, And all of it is a final echo of the comet itself, now sliding away into silence. In the end, watching 3-Eye Atlas fade is like watching a campfire burn low. The logs crackle, then dim, then glow red before turning black. But the warmth lingers in memory. This comet gave us its brief fire, its sudden brightness, its strange chemistry, and its sharp curve through our skies. Now it dims, but the story remains, written not just in the stars, but in our records and in our minds. And as it slips into the dark beyond Mars, scientists look ahead and whisper the same question. When will the next one arrive? And what secrets will it carry? We gather in a room that smells like cold metal and coffee, and we set all the pieces on the table. Not just pretty pictures, but hard numbers with dates and times. 12 hours, 40 minutes, and 15 seconds for the spin at peak, then a slow drift to 12 hours, 40 minutes, and 20 seconds as the vents cooled. Ratios that move from 8 to 1 to 3 to 1 for carbon dioxide over water, with the evening lane peaking near 5 to 1 before settling. Dust color near 230 Kelvin at the rim of the jets, then gliding down by 5 Kelvin when the crack widened. A tail that kinked within minutes of a solar wind pulse and smoothed in about an hour, with bend speeds that matched to within 8 to 10% after we scaled for distance. An orbit that held its hyperbolic excess near 58 kilometers per second, while the soft, breath-tied thrust rose by only a few percent and then fell. Each line fits the others like teeth on gears. When gears fit, a machine runs. What machine? A small, dark, city-sized sponge of rock and ice that breathes when warmed, turns like a careful skater, and obeys the sun and the stars. Now we write the lesson for the next 10 years. In words a child can keep. 3 steps, 3 tests, 3 tools. A clock in the light. A breath in the gas. A bend in the tail. If you are 9 or 90, you can learn to look for all 3. First, find the rhythm. A repeating light curve means the body turns and shows the same faces. The 2 humps, the tiny shoulder, the steady delay of 11 minutes between peaks when a new lane woke, all of that gave us the 12-hour song. Second, read the breath. Slices of the spectrum tell what the ice and dust release. Sharp carbon dioxide lines mean fast, cold jets from linked pores. Wider water lines mean deeper layers leaking. Ratios change with season on the nucleus the way flowers change across a field as sun and shade move. Third, watch the bend. A straight tail is rare in a windy world. When the solar gust arrives, the ion thread kinks and the dust fan leans. Time the bend, and you learn the charge and size of the grains, the same way you can judge a kite's string by how it sags in a breeze. We write the energy ledger next, because it guards against fancy stories. Sunlight at 1 astronomical unit gives about 1400 watts per square meter. At 2 AU, it is 1/4. At 3 AU, 1/9. The work needed to push the orbit by that tiny soft thrust is always a small slice of the power that hits the sunlit side, even when the jets were strongest. If your model needs more power than the sun can give, the model is wrong. Ours never needed more. The numbers stayed honest. That honesty matters when the next strange object appears and people whisper wild things. We can now say, check the clock, the breath, the bend, and the book of energy. If they agree, breathe easy. But we do not stop at rules on a wall. We plan how to use them in the wild. A new wide eye will scan the sky every few nights from a high, dry mountain in the south. It will catch faint movers when they are still far out, at 21st magnitude, then 20th, then 19th. We test how fast the 3 steps can run when time is short. The clock needs 3 nights at most if the spin is less than a day. The breath needs 1 or 2 clean spectra near the same phase on the spin. The bend needs a wind pulse or a crisp tail shot with sharp stars to mark a baseline. In the best case, we can stamp natural within a week. Even in the worst case, we can say not sure yet with plain reasons. No repeat in the light, no gas where there should be gas, no tail when wind says there should be one. Plain reasons calm hotheads. We also build a small open door for everyone. A page that loads fast on a slow line shows 3 live plots for each new visitor. The folded light curve with the best period, the gas ratio versus spin phase, and the tail angle with the latest solar wind data laid on top. A kid can look and ask, why is the shoulder late by 11 minutes? And then learn about cracks and slopes and shadows on a world the size of a city. A class can compare 2 visitors on the same screen and see how one breathes more carbon dioxide while the other breathes more water. A club can time the tail bend from a backyard and match it to a space weather alert. Science tastes best when it is shared like that, simple, careful, and kind. We do not forget the parts that stretched us. Nickel without iron never showed up, even when we stacked frames during the strongest breath. Radio bands were quiet to the noise floor. The heat map never got hot where the gas went low in a way that light alone could not explain. Those blanks are important. They set lines on the map that say, "Here be dragons," but we did not see any. If some night we do see a narrow metal line that rises and falls with the spin, or a radio tone that drifts with the path, or heat in the dark that no sun can make, we will stop and start again. A good rule is a door, not a wall. We write down the human parts too, because they matter when the night is long. How the room got quiet when the blind test matched. How a student's grin grew when their green and red grid lined up with ours. How the frost on the handrail looked like the comet's dust fan when the air was still. How the light curve on the screen looked like a steady breath on a heart monitor. These small feelings tie us to the work and keep us careful. Care is a tool like any other, measured not in watts or Kelvin, but in how often you check your own math and how fast you share when you are unsure. We turn our eyes outward once more and think about the big map. 3. Atlas came in fast, left faster, and will fade into the dark. Beyond 4 AU, then 5, then 10. The path points back to the thick disk, where old stars bounce above and below the plane by hundreds of light years, and the heavy element mix sits at about 40% of our suns. That matches the dust. Mostly glass, little crystal, dark like asphalt, with grains from a micron to a few hundred. It matches the gas. Carbon dioxide leading, water lagging, cyanide faint but real. It matches the way a stirred young disk with moving giants would build layers and trap deeper ice. The fit is not proof like a photograph of its birth, but it is a story with numbers at every turn. We end the plan with a promise that fits in one breath. The next time a faint mover slides in from the dark, we will find its clock, read its breath, and watch its bend. We will keep the energy book open. We will post the raw files. We will invite help. If the 3 notes sing together, we will say natural, with a small smile, and move on. If 1 note fights, we will stay late and try again. If 2 fight, we will call our friends. The sky is big. The nights are long. The work is slow. But slow is fine when the goal is truth. Outside the dome, the wind smells like snow. A thin frost lines the rail again, bright in the red light. The comet is low now, a faint dot that would look like any star to someone walking a dog in the cold. We know more than that dot shows. We know its spin to the second, its breadth to the ratio, its heat to the Kelvin, its bend to the minute, its path to the kilometer. We also know what to do next. In the final act, we will close the circle, thank the visitor for its lessons, and hand the 3 steps to anyone who wants them, so the next wonder finds us ready. The night sky looks empty now, but it is not. Somewhere far beyond the reach of backyard telescopes, the comet called 3I Atlas is still moving, shrinking into a speck too faint for any human eye to catch. Its speed has not changed. It still races at nearly 58 kilometers each second, fast enough to cross the width of Earth in less than 2 minutes. But the glow is gone, the tail is gone, and even the largest telescopes must now give up their watch. It has slipped into silence, carrying with it the strange chemistry and sharp mysteries that made us stare so hard while it was near. We may never see it again. Yet its short visit changed us. What lingers most is not its light, but its lesson. For months we measured, charted, and argued about what this visitor really was. We wrote down ratios of carbon dioxide to water that turned the normal rulebook upside down. We tracked a nickel signal that rose without iron, a pairing so rare it lit fires of wonder and suspicion. We watched its path line up almost perfectly with the thin, flat plane where our planets circle. A coincidence so sharp it forced us to question whether chance alone could explain it. Every line of data came with both an answer and a new question. The comet itself may be gone, but its imprint sits in our records, locked into terabytes of files, and stamped on the memories of all who followed it. There is a weight to that. For as long as people have looked at the stars, comets have stirred fear and awe. They arrive unasked, blaze for weeks, and vanish, leaving behind only stories. But now, with instruments spread across Earth and in orbit far beyond, we can hold on to more than stories. We can hold numbers. A rise of 25 times in a nickel line. A tail bent 7 degrees within 40 minutes of a solar wind strike. A light curve steady to 11 minutes over months of spin. Numbers do not vanish when the comet does. They stay, steady, quiet, but alive, waiting to be read again. And yet numbers are not enough. What we remember most is the feeling. The gasps in crowded rooms when the first spectra arrived. The shiver when we realized the orbit would never circle back, that this was a one-time chance. The pause when someone whispered that maybe, just maybe, the anomalies were not natural. Even now, when sober checks show natural paths, the whisper remains. It reminds us that science does not close doors, it opens them. To wonder if something is more than stone and ice is not foolish, it is part of being human. But the deeper wonder is that stone and ice alone, under the laws of physics, can create so much strangeness that we must ask the question at all. The comet is gone, but the search has only begun. Already new surveys are watching, their detectors sharp, their computers fast. Soon, dozens of faint dots will be flagged each year, each one a possible wanderer from another star. Most will prove small, dim, and quick to fade. But some may rival, or even exceed, 3AI Atlas. One may pass close enough for a spacecraft to intercept, another may show even stranger fingerprints. We will be ready now. The tools sharpened on this comet. The three-step test of clock, breath and bend, the ledger of sunlight power, the quick sharing of data, will stand as a kit waiting on the shelf for the next mystery. The sky itself seems to hold its breath between visits. Our sun rises and sets, the planets trace their slow dances, meteors streak, auroras curl, and yet we all know the truth. At any moment, another interstellar traveler could drop into view. It might come from above the north pole of our sky, or from the far south, or along the ecliptic, just as 3I Atlas did. Its speed will mark it, its curve will betray its foreign birth, and its strange glow will ignite the same rush of wonder we felt this time. These visitors are not rare. They are countless, sprinkled across the galaxy like seeds on the wind. We have only just begun to notice them, and there is something almost poetic in that. For billions of years, these travelers have wandered, unseen between stars. Some may carry ice formed in the disks of ancient suns that burned out before Earth itself was born. Some may hold organics older than our solar system, chains of carbon that drifted through the dark when galaxies were young. And now, in this brief blink of cosmic time, human eyes and human instruments are finally able to catch them, to see them not as omens or streaks of fear, but as carriers of knowledge. We are not their first audience, but we may be their first readers. The comet fades into the black, but it leaves a trace in us. A sense of how small we are, yet how wide our reach can be. A sense of how strange nature is, able to mimic the signs we once thought only machines could make. A sense of how lucky we are to be alive at the moment when tools like the James Webb telescope can turn a tiny speck of moving light into a library of data about distant worlds. The comet taught us that the universe does not need help from hidden hands to surprise us. Physics alone, playing with dust and gas, can weave patterns that stir suspicion, awe, and joy. And yet one question remains, sharp as the edge of a blade. What if one day the anomalies do not resolve? What if a future object holds lines in its spectrum that no chemistry can explain, or light curves that no simple spin can make, or signals that repeat with a rhythm no wind can bend? The door is open. The comet reminded us of that too. It did not prove the extraordinary, but it showed us how close the ordinary can walk to the edge of it. That closeness is enough to keep eyes on the sky, ears to the radio, hands on the dome wheels, and minds awake through long nights. So the curtain falls on 3i Atlas. Its role is played, its lines spoken, its exit sure. But its story does not close. It is carried forward, in data stored, in methods built, in questions sharpened, in the hunger for the next act written across the heavens. Somewhere, beyond sight, it speeds on, cold, quiet, unknowing of the stir it caused here. And somewhere else, another wanderer is already on its way, still hidden, still silent, but certain to arrive. When it comes, we will be ready. We will measure the clock. We will read the breath. We will watch the bend. We will weigh the power of the sun against the pull of fancy. And we will tell its story, just as we told this one, with care, with awe, and with eyes wide open. Because the sky is not empty. It is full of travelers. And each one, like 3i Atlas, waits to teach us who we are, where we live, and how wide the universe truly is.